Today we're going to solve the exam questions from last year. I guess we're going to solve at least 12 problems today. And we're going to go in the same order that as it appeared in the last year's exam. And the first question is, I'm going to solve the first question, and the first question is Boolean logic circuits. All right, so let's get started. So in the first question, the first question has two parts. In the first part, we're given some min-terms, and oh yes, good catch, thanks. If I can find the, all right, very good. And maybe I can hide this one as well. Yep, cool. All right, so we're given, like there are two parts, and in the first part, we're given min-terms, and we are expected to write down the Boolean Boolean equation of these min-terms by also simplifying it, right? So these are mainly 4-bit values, and we can, as we know from the lecture, so we can assign variables to those 4-bit inputs so that we can use them in our Boolean equation. And I'm going to use basically the common terms we've been using, A, B, C, D, and I'm going to use A for the most significant bit and D for the least significant ones. So let's get started. So I'm going to start writing the Boolean expression of the min-terms that are given, right? So if I'm using A for the most significant bit, I could simply write A, B, C, D for the first min-term. And I don't really have to do anything because all of them are ones, and you can assume that there are n's over here. And I'll just basically continue for all of these min-terms over there. So you can, by the way, stop me whenever something is, I don't know, not very clear, although these are relatively easier concepts. And yeah, A, B, C, D, but I need to put a not for D, right? Because I have 0 or A, B, C, D, but the least 3 bits are zeros, or A, B, C, D, and the second and the third one are zeros. A, B, C, D. This one is A, B, C, D again. This one, and last A, B, C, D, all of them are zeros, right? Is that clear so far how I write down the Boolean equation? Perfect. So we want to simplify that, right? And you can either like go from here and simplify it by your own observation, but we could also apply Carnot map, which is easier, which is the easier way of doing it, I guess. So I'm going to apply Carnot map here. So you can also apply Carnot map, by the way, as long as it says that explicitly you shouldn't apply Carnot map or anything like that. For Carnot map, what I'll do is that I'll have sorry. Say it again. Oh, he didn't cover Carnot maps, so you don't know how Carnot map works, I guess. Okay, so I'm just going to do it as usual, which I'm not prepared for. So so what then we're going to do, like based on our observation, I'm going to just disable this one, right? And let's just try to simplify that as we would with the Carnot map, I assume. So what I can do is that I can try to observe the common terms here, and then from there I can go and simplify things. So let's see what sort of common terms we have over there. We have BC, I guess BC knots covered in many places, so I can go with the BC knot. And I have A and D knot. Oh yeah, that's great. Thanks, Giray. All right, so what is the first common? So I guess it goes with BCD even. Okay, apparently we can also have BCD. So the strategy that I'm applying here is that I'm trying to observe the the most common terms in this formula so that I can use them to simplify things, right? So the first strategy is to be able to find those most common terms that appear in the equation. So, and apparently BCD is one of those. So it goes with A and or A naught. And the second most common one would be AC, apparently. And I can have BD B D naught, B naught D, and sorry, there's OR here, and B naught D naught, right? And the other term would be here A B, and I could use C D, C naught D naught, CD, and C D naught. All right, so let's see what's happening here. Is that so? This is so I have A or A naught here, so this is definitely 1, right? So I can simply write B naught, C naught, and D naught. And over there, what I have here, I guess, is AC and or AB. Why is that? All right. So I guess, so this is all possible combinations of B and D, right? So then this means that this is here, that is definitely 1. And same as here, this is also definitely 1, right? Because I have like CD, C D naught, and C naught D and CD naught. So same as here. So meaning that these are 1, and simply I could just write AC or AB naught. And if I wanna, I guess, simplify even further, BCD. So I'll just use a common term over there and CB naught. Okay, this is visible. Okay. And I would assume that it's not okay to apply Karnaugh map in the exam. That's a good catch, yeah. Any questions for that part? Okay. So second question is a bit more tricky than the first one. So we're given a formula, and we want to basically convert it in a way that we only use NOR operations. So for that, there are actually a couple of steps that you should keep always in mind. And then you're going to iterate over these steps to basically check whether like you can apply one of these steps when you're converting your formula to the version that it only includes NOR or NAND. So those steps are mostly usually start with, first it starts with simplification, all right? So when you have an equation, just basically check whether it is simplified enough. So if it is not simplified, so you can first choose to simplify so that like your life is going to be easier solving the question. The second step that we can apply while converting this formula is De Morgan's law. So we're going to always keep that in mind as well. The third one would be, we can always also sometimes apply not operations, right? Because when you apply not, you're keeping everything same, changing nothing, but it sometimes helps us get rid of, like, helps us to actually apply later on, apply De Morgan so that we can either have NOR or NAND. Or the last option would be you can either choose to AND or the equation or the formula or the term with itself, right? So we can always choose to AND or things to itself, and nothing is going to change, but still it can help us to convert things to their NOR versions. So keeping those in mind, I'm going to start. This is all right. This is visible. So all right, I'm going to start. I'm writing down the equation again. BC AC and not here. So when I observe, so the term over here seems okay to me for now, right? This one, because if you just consider this one BC as one input and AC as another input, what I have here is already a NOR. So I don't really want to touch that because it's already relatively in a good form. But what is not okay is this part. Why? Because I have OR of two terms. So I want to basically get rid of that. I want to start with getting rid of that. And so I can either apply De Morgan's law here or not. So in this case, I'm going to choose applying not. So you could either also go with De Morgan, but when you have like too many terms, things get complicated. So not is always easier when you have too many terms. So I'm going to start with that one. BC. I'm just writing down exactly the same thing. Not over here and not over here again, right? So when you look at it here now, so the problem for this part seems to be solved, right? Because I have, let's say, two inputs and they are NOR, but I want to basically get rid of either this NOT or the one that below it, right? So another approach that I can go is either I could apply De Morgan again, or I'm gonna either and or with itself of what I have here. So if I'm going with De Morgan after applying not, it usually is a sign of like going backwards. It's not always the case, but I would be careful if I'm applying De Morgan after not. And so this time, basically, I'm just going to go with like either ending or oring with itself so that I can get rid of the one of these knots over there. So if I do that, so I'm basically just thinking out loud, or I'm going to think out loud while doing so. All right. So over here. All right. So what I'm going to do is I'm going to write it again. Exactly the same thing. AC not, right, and not. So what I did is just write to the self. So, and now I need to decide whether I should end or with itself. And don't forget that I have, let's see, I have one more not here. So if I apply actually or, this means that I have another NOR again. So I don't really want to apply AND because then I will need to apply more operations so that I can get rid of that AND is at itself again. So if I apply OR here, then this means that this looks okay here because I have a NOR for this part and this part. All right, so let me see if everything looks fine. The not. All right, so I have probably one more not here. Let me see. There's a BC not, and I applied not, right? Yeah, I have one more not over there. All right. Let me also check with this part just to make sure. I have AC not and this part. Okay, not. And what I'm doing is basically yeah. So what I'm doing is over there is, yes, I use this not and also this not. Let me see. Yeah, sorry for the confusion. So what I'm copying here is like this part is this part. So this means that I'm moving this knot as well. So this knot should be moved over here. This knot is over here. So if you just ignore this one, so I have full knot covering two terms and knots for these ones. This looks okay now to me. Okay, Yes, it looks fine. All right. So now I guess like everything is solved except for this one, right? Because I have a NOR here. Let me highlight that one as well. So I have a NOR here. I have a NOR here. Again, similarly, I have a NOR here. And in the larger part, I also have a NOR here. So only thing that we didn't solve yet is this thing, A naught, and of course, like BC and AC naught. So it's relatively easier to solve A naught over there because I can simply just, this is A naught, right? So I could apply De Morgan directly to convert it to A or A naught. So I'm just going to do that. And what I'm going to do is as follows: AA naught or BC AC naught, and this is NOR, and same thing again, AA naught. So let's just put one more parentheses, BC AC naught. This is NOR, there should be one more naught here over there. And it's of course like there is one more naught covering all of these things. So that's the outer part. Anything that's not clear so far? Yeah. Oh, sure. Yeah. Cool. Is that better? Cool. All right. So there are two things remaining. And those are, if I can find my red color. Okay. Those are BC and AC naught. So I'm going to solve them separately. And I'm not going to really insert them here. I'm going to solve them separately and assume that like they are inserted in the formula later on. So in order to solve BC, you can again like either apply De Morgan or not. Let's go with not here, right? And this would mean B naught or C naught and not exactly. And in order to get rid of these terms, they're knots, I'm going to apply the similar strategy that I applied for A naught. And this would be, because like this is BB, not, right? So I'm going to do BB not or CC not and not. Yeah. So yeah, everything is solved. I guess I have a NOR here, I have a NOR here, and this is NOR again. And you can assume that this is inserted to here. Similarly, we're going to solve AC naught. Again, we could go either way, either with De Morgan or not. Let's go with De Morgan this time. Let's A or C not, right? And this would mean, so we're applying not here. That would be easier if I went with not, but anyways. AC, I'm going to apply not here. And this would mean that, all right, then I'm going to see. I'm basically ORing with itself. It would be easier if you went with not at first because we're approaching to the same terms. So same. So what I did is just like I ORed this thing with itself. And I guess in order to solve these parts, similar strategy, A not or C not same again. AA not or CC not. Let me check if everything looks good. Yeah. Yes. Yes, everything looks fine. All right, so this is AC not, and you can just assume that we're going to insert this thing here and this one to here, and finally we should have all norths in the formula. And I also observed that once CC, C or C is missing in the solution, I checked whether it can be further simplified, so I couldn't see any other simplification. Maybe it's missing from the solution, but that version should be the absolute correct one. Any questions? Anything? Yeah, go ahead. Exactly. As long as like you're super clear about what you are trying to do, you can just write down your assumption or the way that you're solving the question, and whoever is grading your exam should grade it accordingly. Yeah. Okay, I guess that's all for the first question. What is the question, Joel? I can. Let me see. What we did is A and C, and they're not. Say it again. Oh, yeah. So, but I guess the question is like, can't we simplify the last version further? And the way to do that is maybe student can speak up and then we can hear him or her well for the simplification.
Yes, the question is down there you have not A and C, and then you have not, and then down there you have these multiple not A and so on, but you have to twice.
I couldn't really hear well, but so I'll check the further simplification, and if that's the case, I'll write down in the Zoom or like tell one of the colleagues here so that.
That's actually hard to communicate this way, right? Yeah. Maybe we can continue on Moodle.
Yeah, that's also fine. Exactly, yeah. If you can also write down your answer to Moodle, and then we can continue from there as well. Well, I'll check the simplification. If that's the case, I'll let you know as well.
Okay.
We should also fix the speaker problem also.
Yeah, I don't know how to. Okay. Okay. Is this working? Can you hear me? Okay, I think you can. So we have a question which has a gigantic question part here. So basically, this is about Verilog, which it's the hardware description language that you used in the labs, in several labs, right? So here in this question we have 5 blank spots in this code, and we're trying to fill it in the most appropriate way. So to just get familiar with the module here, let's see what it does. So we have something called anval that we don't have the definition here, so we will provide that soon. And we have two always blocks, right? So this block and this block. So let's say this is A, this is B. You can even draw the circuitry, right? So you can have an A, you can have a B. And if you look at the right-hand side of the equations here, you can see what the inputs of A are. So in the case, we have op, right? So op is one input. We have O data, I data. So these are some other inputs. So these are not really that important for the question itself, but I'm just trying to make you more familiarized with the code itself. And then this always block calculates the value of this anval, right? So the output is anval. And then we have the second always block, which has clock as one input because it's in the sensitivity list of the always block. And we have reset. And we have, okay, so we have some comments saying that here we will reset O data to 0 for the next cycle. So the O data will be an output. And this will assign anval to O data. So it should use anval as an input and O data as an output here, right? So, and you can actually see that anval is assigned here and it's connected to here. And O data is also connected to here. So we have this kind of design here. Okay. And when you look at the inputs and outputs of the module itself, you have clock and reset as input. So let's say we have the module here. You have clock and reset. And I cannot see. Okay. I data is another input. It's actually implicit in the name, but don't get tricked by the name. So it's defined as input. And there's another input called op. So these are like op is 2 bits wide, and I data is 16 bits wide, and clock and reset are just like 1 bit. And then we have an O data, and we know that it is 32 bits, but we don't know if it's output or input. Okay, let's start with like how we're gonna complete this code. So for the first one, so we are gonna put O data either as an input or as an output because it's in the IO list of the module itself, right? And it seems like we are assigning the value of O data in this block, right? So in B. So you cannot basically change the value of an input signal. So it has to be an output here, O data. And basically what you should do is basically define it as an output, right? So you can either put this, or this, but you cannot put this. Okay, so between these three, we should choose which one to put. So O data is not defined as a register or wire in the module itself. So it has to be defined here. Therefore, it should not be output ideally. In some synthesized tools, you can put it just output. Maybe it works, maybe it doesn't, but according to rules, it shouldn't be output. And actually, because of the fact that this value of O data is determined by an always block here, which is the second block, it has to be a register because the whatever is output of an always block has to be registered. You cannot assign wires in always blocks due to the syntax rules. Therefore, it has to be output register. Okay, let's move to the second one. So here we have anval. So anval's value is determined by the first block here, and it's used in the second block as an input. And we see that the initial value of NVAL is a 32 bits long value, right? So it has to be a register and it has to be 32 bits. So it has to be this one. And why it has to be registered? Again, it's registered because the value is determined by an always block. Is there a question so far? Yeah. Okay. So yeah, technically you can write it like, okay, maybe just right here, NVAL, and then 32 bit 0, right? And then this will be just like 1 bit. And the value here on the right-hand side of the equation is like 0. So it will get the value of 0. And if you try mapping some other 32-bit number to here, assigning it another 32-bit number, it will get the least significant bit in the like common use case, let's say, if you write it in that way. But ideally, you shouldn't do that. Yes, synthesizers are okay with that, but to make your design robust, you shouldn't do that, actually. Yeah, does it answer the question? Okay, perfect. So also among these options, we don't have any like other bit length anyway. It's just like all of them are 32 bits. So we need to decide if it's register, input, wire, or int. So it has to be registered because it's written by the always block. Okay. The third one is here. So here we have a case statement here, right? So you can imagine how case is implemented in a way that it's just a multiplexer. Do you remember the multiplexer from combinatorial logic? Okay, I hope you will remember that. So if you actually try implementing this, it's basically something like, okay, you can see this part. This is like a multiplexer, and you have 2-bit select signals here, which is op. Let's say it's like this, op, and it's 2-bit wide. And you have different options here, right? For like all possible values of op. And your output is NVAL. And you assign NVAL to O data plus I data if the op is 0, 0. So it goes to this place, for example. So I hope it's, so I'm not gonna put everything here, but I hope it's clear. So here we have the possible values listed as 0, 0, 0, 1, and 1, 0. So for the fourth one, we can have two options, actually. It can be 1, 1, or syntax also allows you to just write default, meaning that if it is not any of these, it will go to default, right? So let's see what we have here. So we have this 2-bit binary 3, which is completely illegal, actually, because if you put B here, you need to write the number next to it as in binary form. And in binary, you only have 0 and 1. You don't have 3. So you cannot actually write it. This is 3-bit 3, and it's binary. It's also wrong because, again, the same reason. And here, this H means hexadecimal. So when you have 2-bit number, in hexadecimal form, the value is 1, 1. So if you remember hexadecimal, let's say this is a hexadecimal number, 1, 1, right? So when you convert it to binary, it will look like this. Because each digit goes to like 4 bits. So this will result in, since you define it like 2-bit long, it will get probably get the least significant 2 bits, and it will map to this 2-bit 0, 1 actually, which is wrong. So you cannot do this as well. So you cannot do any of these. And you have the option default here. So it works just fine here. Okay, so let's move to the fourth and fifth. So here, if you remember, there's a difference between always blocks that are triggered with any input and that are triggered with the passage or nail edge of some signal, in this case it's clock. So if you clock gate these always block, then it's a convention in Verilog that you have to use these non-blocking assignments. If you remember, there were different assignment types. So if you just use this equal, just like here, it's a blocking assignment. That part of the code goes sequential. But you don't want to have that sequential method in the clock triggered circuitry because you need to run it as fast as possible and as parallel as possible. So we also have non-blocking assignments written like this. So we need to go for these ones. And of course, in always block, you just write the name of the signal and then the value. So here we have assign statements, for example. So maybe you remember writing assign in your Verilog codes. You write assign if you're writing it outside of a always block. If it's inside an always block, you don't use assign. So these are wrong. These are wrong. So we have these options here for 4 and 5. So for 4, it should reset O data to 0. So this one resets O data to 0 in a non-blocking way, right? And what does this one do? It just compares if O data is 0. So it's like 2 equal sign, meaning like if statement, right? So it just checks if it is equal. So this is not what we are trying to do. So we get rid of these as well. So for 4, you need this non-blocking assignment here. And 5, you have this non-blocking assignment here. So this is the first part of the question. Is there any question? Okay. Is someone checking Zoom chat? I cannot see it here. Okay. Perfect. So, okay, this is one of my favorite types of questions. What does this code do? So we are just gonna see, try figuring out what does this do. So here, again, we have 2 always blocks and 1 assign here. And if you consider this as a sequential logic, you have the sequential part, you have the combinational part, and you have some output circuitry here, actually written in 3 different parts. So this part is the sequential logic, which actually you can consider this as like a flip-flop here, right? And or some sort of latch, basically. So output is state, and so maybe you're not familiar with this syntax. Let me explain it a little bit. So if you have, so out here is a 2-bit signal, right? If you write, I couldn't write, like this, then this means this is equivalent, let's say, to feed in all bits in out into an AND operation and get in the output. So you AND all the bits in out. So this therefore just evaluates 1 only if I run if I write down the truth table here. So for out value 0 0 0 1 1 0 1 1, right? All possible options we have. So the okay, and out result will be for this 0, for this 0, for this 0, and for this 1. Okay. So this will only evaluate 1 when both bits are 1. And this ternary statement tells us that if the condition here is true, then assign this value. If it is false, assign this value to left-hand side of the equation. Okay, not equation, the statement. Okay, so it means that there is something called state, which is 1 bit long, and it starts as 0, and it is inverted if this out signal is 1, 1. And in all other cases, it just keeps its previous value when a clock signal hits. So, okay, and here it's relatively more straightforward. This also works with clock, and it checks the value of the state. If state is 0, then it increments this myrag. And if the state is 1, it decrements myrag, and both operations are by 1. Okay, and output is directly connected to, excuse me, myrag. Okay, so the question asks us to run this circuitry for 16 consecutive clock cycles from the very beginning, and show the value of out signal here. Okay, so so I'm just gonna write it down here. So we have clock at 0, okay, and we have the state, we have myrag, and out is connected to myrag, so it will be the same anyways. I think I'm not missing anything here. Okay, so in the very beginning, the state is 0, right? And myrag is 0. Therefore, out is also 0. Let's write it in binary form. So these are 0, 0, 0, 0, and state is 0, clock is 0. Okay. I move to the first clock. So when the clock hits, we will run this always block and this always block in parallel, meaning that the result of one is not going to affect the other one in the same clock cycle. So here, out is 0, 0. Therefore, this will just keep the previous state, and my state is going to stay at 0. And state was 0 in the previous clock cycle. Therefore, my rate is going to be incremented by 1. So it will be 0, 1. And output is directly connected to my rate. So it will be 0, 1 as well. And let's move to the second one. So here, my rate out is 0, 1. Therefore, the state will remain as 0 because of this, right? Because, yeah, this is not satisfied, then state is going to stay the same. And this will increment by 1, and then this will follow my rate. This is increment by 1 because state was 0 here. Okay. Now I think things are going to get a little bit more interesting. So here in the third clock cycle, we look at let's look at the state. So okay, it's not interesting still because it's 1, 0 here out. So this value is going to be 0 again. So we are going to maintain the previous state. So state will be 0, and my rate will increment again, and it becomes 1, 1. And when my rate becomes 1, 1, our output is also 1, 1. Okay. Now things get more interesting. So here, output is 1, 1. Finally, this and out signal here goes to 1. So when this goes to 1, state will be inverted. So the state will be 1 here. So we inverted here. And here, to calculate my reg, I will still use the state from the previous clock because those two always blocks run in parallel. Therefore, I will try incrementing this. So when you increment a 2-bit number with value 3, what you get, you normally should get 4, right? 3 plus 1 is 4, but it will overflow in the most significant bit. So you will have 0, 0 here. Okay, is that clear? And when this becomes 0, 0, output is also 0, 0. Now output is again not 1, 1. Therefore, we maintain the state here. And therefore, we need to decrement MyReg. And when you decrement MyReg, so here your value is 0. So 0 minus 1 is minus 1. So what you get in binary form is again 1, 1 here. Okay, so the output is also 1, 1. And when output is 1, 1, in the next state, you will invert the state. So state is going to be 0. And to calculate MyReg, we need to look at the previous state again, because those always blocks are parallel. So it will decrement MyReg. So MyReg will be 1, 0. And when this becomes 1, 0, output also becomes 1, 0. And when output becomes 1, 0, you will maintain the current state in the next clock, and it will be 0. And when this is 0, you increment this again, MyReg, and MyReg goes from 1, 0 to 1, 1, and output also goes to 1, 1. So I guess you start seeing some pattern here. If you look at in decimal form, maybe it's more clear. So I'm going to write out in decimal form here. So it's 0 here, 1, 2, 3, right? And then it goes back to 0, and then 3, and then 2, and then 3. And if we run one more, what will happen? So here, output is 1, 1. Therefore, you will invert the state. This will be 1. And the state was 0 in the previous clock cycle, so you will decrement it, and it will go to 1, 0. Therefore, it will be 2 again here. So what happens is, until this point, maybe you can consider that as an initialization process. Did I do something wrong? Let me double check. Maybe I missed something. So here 2. Oh, okay. I missed this one. So it was state 0 here. So the MyReg should be incremented. I decremented it. So you need to increment from 1, 1. So this becomes 0, 0. So this is 0 again. And then in the 9th one, since this is 0, 0, this will not change. And then this will be decremented. So it will be 1, 1. And then the output is going to be 3. So every 2 clock cycle, you invert your state. So it's going like 2 up, 2 down, 2 up, 2 down in the output, right? So what pattern you see is it goes from 0 to 3, and then 2, and then 3, and then 0, and then 3, and then it will go to 2 again here, and then 3 again here, and then 0, and then 3 again, and then 2. So you will see this kind of pattern. So I'm not going to continue doing this. You can, if you're not convinced that this pattern is repeating here, you can just try seeing it yourself. But this is the answer, basically. And if you look at the solution, actually, there's a huge paragraph explaining this, but I tried explaining it in a more intuitive way. So I hope this is helpful. Yeah. It is correct if both always blocks are triggered with post-H clock. Okay, this is a bit crowded now. Maybe I should show it here. Where's that? Okay. So yeah. So when you look at the sensitivity list, both of them are triggered with post-H clock. So they should get the value from the, like, before post-H clocks comes. So even though their outputs are connected to each other. So it's basically like this, right? So let's say this is A and this is B. You have A here, you have B here, and both of them are triggered by clock signal. And you use A's output as B's input here. So when the clock hits, it gets the value here and then writes it here, right? And at the same time, B gets the value here and writes it here. Just consider that, like, to simplify things, just assume that these are two D flip-flops. Therefore, the value here does not propagate until this wire, until like 2 clock cycle passes. Therefore, you have to use the value from the previous clock cycle for this D flip-flop. Yeah, so if you so then if you consider that what kind of circuitry it should try implementing. So A assigns, let's say we have state here, right? A assigns a value to state, B assigns another value to state. So there's a conflict here. So you don't know which one is going to be here. Actually, if you try doing that in Vivado or ISE, then you will get a warning or error saying that this is the signal is driven by multiple sources. Sure. Other questions? Okay. Then that's all for me.
Are doing finite state machines. This should be hopefully the easiest of the exercise in the exam. So easy points. It's mostly a question of reading the problem statement right and not making stupid mistakes. So let's go through this. You're given this Mealy machine. Just one input bit, one output bit, and you should try to simplify it and reduce the number of states. So you should explain each step and draw the thing. And well, okay, this is the sentence, if not, and so on. But let's try to do it first. So we should try to get to fewer states. And the first step is probably to check, is anything useless in this machine? So a useless state would be one that's never reachable. And we can immediately see C does not have an input edge, actually. So this one can never be reached. We can remove it. And of course, also the outgoing edges from C would never be used. So the question also asks to write out an explanation. So we do that. C is unreachable. So for your benefit, I will be very short in my writing here. So maybe you can write in the exam a bit more than just 3 words. But you know, say something like, there's no incoming edge, it's unreachable, can be removed. Okay, so after we removed C, now we actually can repeat the same step. Now D is unreachable, the same reason, and it's outgoing edges as well. So afterwards, D is unreachable. Okay, and now we are left with a fairly simple automaton. We can try to remove more states, but as you can see here, somehow in state A, we behave differently than in state B, because for the input bit 0, we output the 0, while over here for the input bit 0, we output a 1. So we cannot combine these states for sure, and the automaton cannot be reduced further. So as the final step, we should draw the resulting automaton. So this is A, self loop, reset, don't forget reset. Okay. I apologize for my terrible handwriting, but hopefully it's legible. Right, so for the second step, you should try to execute some steps in this automaton. So we process binary numbers, and it's important that we go from the, actually you have to be careful about the bit order. So we go from the least significant bit to the most significant bit. So you get this input string, and what's important here is this specification here means that you read it from right to left, which could be an easiest mistake in the exam. So you read it like this. It's specified from least significant to most significant. And now we should just calculate what the output stream should be. So we can go up here and check in the machine. We start with a 0. So we go to a 0, we stay in A. We go to another 0, we stay still in A. We go to 1, we go over to B. Now we get a 0, and actually each input bit now gets inverted. So any one input bit becomes a 0, any 0 input bit gets a 1, while before in A we did not invert the inputs. So let's see, and as long as we only got zeros, we did not invert the input bits and gave them directly as output until we get the first one. The first one we still print as a 1 to the output, and afterwards we invert every bit. So let's, you can write this as an explanation, but the exercise doesn't require it. You can just manually execute this FSM or get this intuition. But anyway, whatever you do, you should get to 0, 0, 1. So these are the first 3 bits. We're still in A. With this one, we go over to B. And now we invert every further bit. So let's see, next 0 becomes a 1. The next one becomes a 0. And 1, 0. All right. That's that. Simple enough. Is there any questions so far? No? Great. All right. So again, it's mostly a question of reading the question precisely. So you should design a more type machine, which, by the way, they gave this nice hint here. So recall that the output depends only on the current state on the Moore machine. So the previous exercise, we had outputs for every edge. Here we need to design a Moore machine which has an output for every state, because it's a Moore machine. Okay, so let's see, the input is again an unsigned binary number, and we get it as a bit serial fashion. But interestingly now, we get it from the most significant bit to the least significant bit. So you really need to read this carefully in the exam, because this time it's from left to right. So let's see, the output should be a logic 1 exactly if the input so far is divisible by 8. Okay, we got everything. So they gave some examples here for which inputs this should be a 1. Let's see, so divisible by 8 really means the last 3 outputs. So for the 1s, the 2s, and the 4s are all 0. That's why you can see in these examples here that really all the ones that you should accept are, have this end in these 3 zeros. Right? if any of these 3 bits were a 1, it would be maybe an odd number or a number that has a 2 in it or a 4. And as soon as you find these 3 zeros, you can be sure it's divisible by 8. The way to define it also, like a 0 by itself is also divisible by 8 because it's 0 modulo 8. So that's all the question reading we have to do. So we should write an explanation also for the FSM we're designing. So what we should write down is something like, okay, we had this insight that we detect the 3 zeros at the end of the inputs. And yeah, you should write this a bit more precisely than I'm doing it right now, and maybe a bit more. You should also explain the exact states. So we should design an FSM that has, basically can detect this. So you have maybe a state S0 that holds all values that are divisible by 8. So these would be ones that end in 3 zeros. And if you from this state go and get next a 1, let's say, then we could call the state S1. Just the intuitive labeling is a 1, maybe, our intuition for it. Okay, so we go here as soon as we read a 1 as the next bit. This would mean that we went from something that's divisible by 8 to something that's no longer divisible by 8 because it just became an odd number because we read a 1. Now, if from this state you read another 1, nothing interesting happens because you are still not divisible by 8. And from this state, you could go to a state S2, which would mean the current bit you read so far ends in 1 0. So you go there. And from here, if you read another 0, maybe go to state S3, which means you end in 1 0 0. Okay. So on a 0, and if you read 2 zeros already, and now you see another third 0, then we are divisible by 8 again. All right. So far, so good. Now we are missing some edges here. So we need a reset edge because as we defined up here, 0 by itself is divisible by 8. So that's where we start. We are initially divisible. And if we are initially divisible, we remain divisible if we add more zeros. Let's see, if we so far read 1 0 and we read another 1, we are again no longer divisible by 8, and we most recently read the 1. And if we read 1 0 0 and read another 1, we also will not be divisible by 8 for some time. Okay, so it's important to have defined what the output edges are for each input, and define the reset edge. And what's still missing now is the output bit. So the output bit should be logic 1 exactly if we're divisible by 8. This is the case exactly here. So output O is 1. Output O is 0 here. Output O is also 0 here. Output O is also 0 here because we're not divisible by 8 in any of these states, and we are divisible by 8 here. All right. Yeah. The exercise asks for an explanation of these states. You should probably give an intuition what this 0 0 0, 1 0 0, 1 0, or this 1 here means. You can of course rename them to whatever is most intuitive to you. Yeah. Is there any question? Trivial, right? All right. Yeah, hopefully this exercise works well in the exam. Then I'm done here, and next person.
Can you hear me, Mel? Okay. Cool. Yeah, I believe you should get full credit from this simple questionnaire. By the way, I'm Jisung Park, a postdoc in Safari Research Group. Let's dive into the 4 questionnaires. So yeah, let me lead the question first. So a new CPU has 2 comprehensive user manuals available for purchase, which describe the ISA and the microarchitecture of the CPU respectively. So unfortunately, the manuals are extremely expensive and you can only afford one of the 2. If both the manuals might be useful, you would prefer the ISA manual since it is much cheaper than the microarchitecture manual. So for each of the following questions that you would like to answer, decide which manual is more likely to help. Okay, so basically this question is asking if you clearly understand what the ISA and microarchitecture manuals should describe. So let me briefly recap the ISA and microarchitecture. And by definition, the ISA is the interface between program and hardware, right? So, and in this program is not just only the high-level programming language such as C++ or Java. It should include any programs. So on top of hardware like assembly code or even machine code, machine binary code, right? So typically at the end of the program layer, we describe the program behavior, meaning the hardware behavior using instructions, right? So ISA should define the type of instructions that are supported by this hardware and also the format of instructions. But how to implement, exactly execute the instructions, the ISA manual does not have to specify them. Okay. Yeah. Okay, let's go over the question now. So the number of uniquely identifiable memory. So yeah, before we go over each question, so my point here is that I would suggest you think about the necessity of the given information in each question here from the programmer's perspective. If the information is really necessary for a programmer to implement a code, then it should be described in ISA in the ISA manual. But if the information could be useful to optimize the performance of whatever of your program, but is not really essential to make a program itself, then the ISA does not have to specify. Okay. So number of uniquely identifiable memory locations, it means the memory space, right? And a programmer should be able to specify the exact location of each variable, programming variable. So this should be properly described, defined in ISA. Hope it is clear. And the number of instructions fetched per clock cycle. So this can vary depending on the exact microarchitectural designs. So if you recall the assembly code, we took a look in course. Yeah, there is no specification in our assembly code, right? So it can vary. So this should be. So the ISA manual does not have to specify this, and support for branch prediction hints conveyed by the compiler, meaning that the compiler, when the compiler generates the final code, machine code, to use this branch prediction hints generated from the hardware, there should be a way for the compiler, it's a software also, right? to get such information from the hardware, meaning there should be some dedicated instruction. So ISA should specify that. And number of general purpose registers, for sure, it should be described in ISA, because a programmer should be able to specify the destination and source registers. But the next, the number of non-programmable registers. So literally, these are non-programmable. So there's no way for a programmer to specify the use of this non-programmable register. These are used for some other optimization inside the hardware. So yeah, it does not have to be specified in ISA. And SIMD processing support. I think this question is a tricky one because usually SIMD processor, even if a processor supports SIMD operations, the processor should be able to run a program that does not have any, meaning that any SIMD processing features, meaning that a programmer should be able to design a program that does not use any SIMD features, right? But to correctly use this SIMD processing features that supported by the hardware, the instruction, there should exist some instruction dedicated to SIMD processing. So it should be specified in ISA, right? And number of integer, arithmetic, and logic units. So again, so this is how to execute, efficiently execute some arithmetic or logic instruction. So it can vary across the different microarchitectural designs. Okay, and number of read ports in the physical register file. Yeah, typically you may already know. In our common program, such information is not included in our code, I would say. So this also should be, so does not have to be specified in the ISA for sure. So the point is that, yeah, you may be able to say that, okay, so there could be some instruction set architecture and microarchitecture manuals, which is a very simplified or in the opposite, very they can provide us very micro controls in ISA level, but we are talking about common principles, right? So thinking about so questioning the common principle is definitely good for research to advance the technology. But in this question, we are talking about the common principle. So endians, I assume that you clearly understand what endianness is, right? So because the programmer should be aware of the big endianness used in the certain hardware, because otherwise the machine translates the value of the certain value in a different way we intended, right? From we intended. So it should be specified in the ISA manual. And size of a virtual memory page. And yeah, typically in common CPU architecture, the instruction always deals with an instruction always deals with virtual memory address, and the address is translated to physical address, and it involves a lot of hardwares typically. So there is an agreement between the programmer and the hardware itself, so that the virtual memory translation is correctly done as intended. So this should be also described in the ISA. And cache coherence protocol and number of cache blocks in the L3 cache. These are not necessary to be specified in ISA, because the cache implementation, this is implementation to tolerate the long memory latency. So it depends on the microarchitectural design of the CPU. But ability to flush a cache line using the operating system code, meaning that to figure this out, the programmer needs to know, right? So it's kind of also contract between the between a programmer and the hardware. So it should be specified in ISA. And number of pipeline stages, again, this is implementation. We already covered various possible pipeline designs, like multi-stage and pipeline execution. So there could be only one pipeline stage even, right? So this should be found in microarchitectural manual. And last, how many prefetches the hardware prefetcher generates in a clock cycle? Yeah, this is also implementation of the memory request, right, to optimize the performance. So this does not have to be specified in the ISA manual. Hope everything is clear. So do you have any question? Thanks.
Okay, this is my time. Can you hear me well? Jen, I cannot hear you. Hello, hello, can you hear me? Jen, I cannot hear you well. I don't know if you're saying something. Okay, can you see my iPad? Okay, so I'm going to start then. Can you make it bigger? I don't know how. Maybe I can zoom. If this will help. Is it better? Okay, looks better. Okay, so I'm going to start. So this is the performance evaluation question. This question first. So here we're having a multi-cycle processor P1 that executes load instructions in 6 cycles, store instructions in 6 cycles also, arithmetic instructions in 2 cycles, and branch instructions also in 2 cycles. And then you have application A, where we have a breakdown of instructions. So you have 40% of all instructions being load instructions, 20% of all instructions being store, and 30% of all instructions being arithmetic instructions, and 10% of all instructions being branch instructions. So the first question here is asking what is the CPI of application A when executing on processor P1. So CPI, if you don't record, means cycles per instruction. And we are interested here on the average CPI for the application, right? So for you to calculate the average CPI for that application, we are going to simply multiply and add all of those cycles that it takes per instruction and the amount of instruction that the application is going to execute in the application. So it means that first we are going to see the application executes 40% of the instructions are load instructions, right? So that means that you're going to multiply 0.4 times the latency that it takes in cycles of load instructions, which is 6 cycles. So times 6 plus, and then you repeat for each instruction type. Then you have 20% being store instruction, so it's going to be 0.2 times the latency of store instructions, which is also 6 cycles, so times 6, plus the amount of arithmetic instructions, 30%, so 0.3 times the latency of arithmetic instructions, which is 2 cycles, so times 2, plus the branches, 0.1 over here, times the latency of the branches, which should be 2 cycles. So here we have this number of cycles that is going to take for load instructions, for store instructions, for arithmetic instructions, and for branch instructions. And if you do this math, I guess it should give you 4.4. So this is the final value. Is there any question related to this in the audience? Okay, I'm assuming there is none. And then in part B, it says that a new design of the processor is going to double the clock frequency of processor P1. However, the latency of all instructions increased by 4 cycles. We call this processor P2. The compiler used to generate instructions for P2 is the same as in P1. Does it produce the same number of instructions of program A? This is all of this information is going to be important for the next question. What is the CPI of application A when executing in processor P2? So pretty much we do the same thing. So CPI, but now the breakdown of instructions stay the same because it's in the compiler is generating the same number of instructions. The only thing that is changed is that we are going to increase the number of cycles for each instruction by 4. So now you're going to have here 0.4 because these are the number of load instructions times. Now the latest that is going to take for load instructions is going to be 6. What was the original latency here? Plus 4 because we are going to increase the cycle of all of the instructions by 4. Then we do the same thing for the store instructions times the original latency was 6, we increment it by 4. And then for the arithmetic instructions, the original latency was 2, we increment it by 4. And finally, the branch instructions, the original latency was 2, and we incremented by 4. And I guess this should give you 8.4 if I'm not mistaken. Any question related to this? There is something in the chat. How much would be get deducted if you got the wrong result by calculating errors, but not the formula? Okay, so usually I'm the one grading this question, so I don't deduce much if you do math mistakes. Like this is 10 points, right? I would deduce like 1 point or something, depending on how bad is the error, or if I can clearly see if the error is a math mistake rather than formula mistake, like meaning if I understand that you know the formula but you just multiply something wrong, I would not deduct much at all. So it's really important when you do this performance evaluation question to first write down the equation, similar to what I did here in the first part, breaking down each part of the equation. So the TA that is grading understand that you managed to, you know exactly what you're doing related to the equation itself. And then when if there is an error for math later on, the TA would know to not deduct much for that, because what we want to evaluate is if you understand the concept, right? What CPI, for example. So yeah, I guess this is. I guess this answers the question. Okay, so I'm going to go to the next question. So it's asking which processor is faster and by how much. Sure. And then the most important equation here is going to be the equation for execution time. Execution time. So execution time, if you recall from the lecture, is equals to the number of instructions that the application executes times the CPI times the 1 over the clock frequency. So if you apply this equation here for application for processor 1, we are going to have the execution time is going to be the number of instructions times CPI of processor 1, which is 4.4, times the clock frequency. Just put F here. And the execution time of processor 2 is going to be the number of instructions executed. Recall that in the previous question we said that the compiler used to generate the instructions for processor P2 is the same as P1. Thus, it produces the same number of instructions of program A. So it means that this instruction here and this instruction here is the same number. Times the CPI of processor P2, which is 8.4, times the frequency. So a new design operator doubles the clock frequency of processor P1, right? So if this frequency of processor P1 is F, these other frequencies here is going to be 2F, right? So if you simplify, if you divide one equation by the other or simplify the equation, we can see here. So this instruction is the same as this instruction, right? This 1 over F term here is the same as this 1 over F term here, so you can cut. So we are going to have that this is going to be, we can say that this is 4.4, and this is 8.4 divided by 2, which is 4. This is 4.2. So execution time, lower is better, right? So the execution time of after the simplification of the execution time of processor P1 is something is in the order of 4.4, while for processor P2 is 4.2. So it means that processor P2 is faster than P1. Again, recall that execution time lower is better. And by how much? We just divide 4.4 by 4.2. And I don't exactly remember the number from that this gives. This is 1.05 times. So yeah, this is basically how you solve this. Is there any question related to this? Okay, so in the performance evaluation question, this equation here is your best friend. So don't forget this equation. Okay, so last part of the question. So you say here that you want to improve the original P1 design by including one new optimization without changing the clock frequency. You can choose one of the following optimizations. So ILU, so you're going to have an optimized ILU, which halves the latency of both arithmetic and branch instructions. So both arithmetic and branch instructions. Or LSU, arithmetic load store unit, with halves the latency of load operations, but doubles the latency of store operations. So which optimization should you add to processor P1 for application A? So there are many ways to solve this question. So you can apply the execution time formula here for the two optimizations and see which one would be best by calculating the CPI again. So this is one way, but I'm going to use another equation here that we learned in lecture 20, if I'm not mistaken. So which is Adam's law. So we have from Adam's law that the speed up that you can get for optimizing something is going to be equals to 1 over 1 minus the enhanced fraction. So usually we call this 1 minus p. So p here is the portion that you are enhancing, plus the port p, which is again the portion that you are enhancing, and the speed up that you are providing by to the enhanced part. So again, you can check lecture 20 for this equation over here. So we are going to apply this formula to see which speed up is larger. So let me just copy from the previous from the breakdown of instructions of application A. We had, if I'm not mistaken, 40% of load instructions, 20% of store instructions, 30% of ILU structure, arithmetic instructions, and 10% of branches. Okay, so let's apply that formula over there. So the speed up is going to be, or first for the ILU optimization, is going to be equals to 1 over 1 minus the portion that you are enhancing. So the ILU part, you are enhancing both arithmetic and branch instructions, right? So how much, what is the portion of arithmetic and branch instructions that you have in the application, right? You have the 30% arithmetic instructions and 10% of branch instructions. So it's going to be 1 minus 0.3. I'm going to simplify this. It's going to be minus 0.3 minus 0.1. Why again? This is coming from the fact that we have 30% arithmetic, 30% of branches, plus the portion that you are going to speed up. So you are speed upping 0.3 plus 0.1 of your application, divided by how much you are optimizing that part, right? By how much you are optimizing that part, so you are halving the latency, right? So you are optimizing the part by 2 times. So this is divided by 2. So if you do this math here, this should give you 1.25 times. And then we do the same for the LSU part. So 1 over 1 minus the portion that you are optimizing. So you are optimizing load and store instructions. So load instructions are 40%. And store instructions are 20%. let me highlight this again. So this 0.4 is coming from here, and this 0.2 is coming from here. Plus the portion that you are optimizing, 0.4 plus 0.2. Oh, but there is a fee. So for this is an asymmetric optimization, right? So for the load operations, you're halving the latency, right? So load operations are 0.4 of the are 40% of the total that application, right, or instructions that you have. So for those 40%, you're going to halve the latency, meaning that you're optimizing by 2 times, right? The latency of load operations. However, sorry, for store operations, which are 0.20% of the total, so 0.2, the latency increases by 2 times, it doubles. So this multiplies the latency by 2. So you could also think of this second part here as if you want to follow the same procedure as before. If this is 0.2, and the latency is times this, right? 1.5 is the same. But anyway, so if you do the math over here, you're going to get 1. So the question is, which optimization do you add to processor P1 for application A, right? So you want to add the optimization that gives you the most speed up. And the optimization that gives you the most speed up is the ILU optimization. ILU optimization, since it gives larger speed ups. So any question related to this? Again, you can, if you don't remember this equation here from lecture 20, you can do the same with CPI. So you calculate the CPI for the LU implementation, the new CPI for the same as we did in A and B here. CPI for LSU implementation, and then you compare the two CPIs. But I want to show how to do it, use this other equation here, which is actually, I guess, is easier, it's quicker to do. So, okay, is any question? Okay, so I guess I'm done. Thank you so much.
Hello, everyone. Let's take a look at question 6, pipelining from last year's exam. So first, let's try to read the question. It gives us a simple MIPS machine, which has 5 pipeline stages, as we discussed in the lecture. So it has a fetch stage where it fetches the instruction from the instruction memory, the decode stage where it decodes what the instruction is, and also fetch the register operands. In the third execute stage, it does the arithmetic operations and generate the memory addresses if it's an load and store instruction. And the fourth memory stage, it will try to load from the memory if it's a load word instruction. Finally, in the write back stage, it writes the register, it writes the result back into the register, or like it stores into the memory if it's a store instruction. Given this basic ISA, we are given 2 machines, A and B. So for machine A, it says it doesn't implement interlocking in hardware. So we, as the compiler, will have to insert NOP instructions manually such that the data dependencies between the instructions are respected. And it has internal register forwarding. In other words, if an instruction writes to a register, then another instruction can also get like this newly written register value in the same cycle. Finally, for the branch prediction, it predicts all branches as always taken, and the next program counter will be available after the second decode stage. And for machine B, the internal register file forwarding and branch prediction are all the same as machine A, but the difference is machine B implements hardware interlocking with data dependence detection. This means that we will no longer need to manually insert knobs as compilers, and the hardware will start the pipeline if it detects the data dependency. And it's worth noticing that the result of a load instruction can only be forwarded from the write back stage. Then let's take a look at the code segment that we'll analyze. So basically, it executes in a loop. So first, it loads two values from the memory address stored in register 4 and write them back into register 1 and 2. Then it adds the value stored in register 1 and 2 and save it in register 3. Then it stores the value in register 3 back to the memory address indicated by register 4. And then it subtracts the value in register 4 by an immediate value of 4. And it continues a loop if the value in register 4 is not 0. And from this initial register values given, we can see that the loop will execute 100 times. So then let's take a look at the first question. So it asks us to rewrite the code segment with minimal changes and minimal latency such that the code can execute correctly with all the data dependency handled. I think it's this question A is the best to be solved together with question B, where it asks us to fill the table with the timeline of the execution of the first loop iteration of the code segment. So let's start with drawing the timeline of the execution of the instructions in the first loop. So first we'll execute this. We'll execute this load word in instruction. So we write this down: load word from offset 0 in register 4, and this doesn't have any dependency, so we can execute all stages. Also for the second load instruction, it also doesn't have any dependency, so we can execute this. Okay, now for the third instruction, as we can see, its two source operands, register 1 and 2, they depend on the previous two load word instructions. And by the third cycle, they are both not ready yet. So let's see when will the value in register 1 and 2 ready. It's at the sixth cycle. So because the value for the instruction is fetched in the decode stage, this means that we will place the decode stage of this add instruction in cycle 6. And if we put a decode stage here in cycle 6, then we see apart from the previous decode stage, we have two empty cycles. So this means that we'll have to insert two knobs here, and the add instruction goes here. So the decode stage is here, and these two knobs just. Okay, then we know that. Oops, sorry. Then we know that we will have to put two knobs after the first two load word instructions. And we put the add instruction. So let's continue with the rest of the program. The next store word in instruction, its source operand also depends on the result of the add instruction. So again, we will have to wait for the add instruction to have the results ready in the write back stage. So same as before, we will put like the decode stage of this stored word instruction in cycle 9, and cycle 9 is like 2 cycles apart from like the previous decode stage. So again, we insert 2 knobs and put the store word instruction here. Yep. Then we also know we need to put 2 knobs here and the store word instruction. And then for the subtraction, we have no dependencies compared to like the previous store word instruction. So this can be safely executed. And finally, for the branch instruction, it depends on the previous subtraction instruction. So yeah, again, we wait for 2 cycles. We insert 2 knobs and put the branch instruction here. Okay, knob. And put the label back. Okay, so we are done with question A and B. Let's take a look at question C. So it asks us, given the rewritten code segment, yeah, please. Yeah, so I think so like this is a bit like ambiguous in defining like what is the first iteration. So you can put like a knob after that or not, because yeah, like you're referring to question A, right? Yeah, so yeah, so in fact, like the start of the second instruction, like it will happen at like the second cycle after like the branch not equal 0 instruction. But yeah, I think in this case, like so yeah, like we have branch prediction here. So it says it's always taken. I think we should have a knob here. But because like this knob is like always there, like regardless of what instruction it is, because like the branch prediction is implemented this way, it's always there. So yeah, because like it's specified that the next program counter will be available after the decode stage. So there's always like a bubble there. Yeah, I think in the case of this question, as it's like as the specification of the machine here, it is this case. So in this case, if the branch if the branch predictor specification is written as this, I think it's like the case that, or like if you put a knob here, we understand like this, it should be okay. Yeah, that's very good question. Thanks. Please. No, because like if we move this up, then for like the store word instruction, it will like write to a different address. Then like you're changing the instructions, not reordering. Yeah, but like in yeah, like this kind of optimization is like legit. You can do that, but yeah, I think in like in designing this question, we do not think that you can rewrite the. Yeah, that's it. Okay, let me read the question again. Yeah, I think we should have written this question better. Because like first in the machine specification, in the data forwarding and interlogging part, it says like the compiler will order the instructions, not like rewrite them. Yeah, but you're right that in question A, we put the word rewrite, so it might cause some confusion. We all like discuss this, and yeah, maybe we will release a better version of the question and we will notify through Moodle. Yeah, but indeed, if you change the instructions the way you did by moving the substruction up and also like change the offset to the store word instruction, yeah, I think it can save some cycles. Yeah, thanks. Okay, so let's continue with like the assumptions that we do not change the instruction themselves, and just like reorder them. And let's take a look at question C to calculate the number of cycles it takes to execute the code segment on machine A. So we have our timeline of the execution of the first iteration here. So as you can see, it takes 13 cycles to finish the one iteration, because as talked before, the first instruction of the second iteration will happen after the decode stage of this like branch instruction. So let's assume like the second iteration happens here. The fetch will be here. So it takes 13 instructions to perform one iteration. Sorry, it takes 13 cycles to perform one iteration, and we have like a total of 100 iterations. So it's 13 times 100. And at the end of the last iteration, we have to drain the pipeline. We have like 3 more cycles to go. So plus 3 equals 1300 and 3 cycles. Yep. Okay, and then for question D, so now we are, yes, please. Yeah, so like in the last iteration, like we're at like cycle D, like cycle 13 D. Yes, then we have like 3 more cycles. Yeah. Okay, now for question D, we are executing the same code on machine B. So machine B, the result from the memory stage or the write back stage, they can be forwarded to the execute stage. And the result of a load instruction can only be forwarded from the write back stage. So it's important to notice that in machine B, the result is forwarded to the execute stage, but not the decode stage. So still, let's draw the timeline. For the first two instructions, they don't have any dependencies. So we can execute. But for the third add instruction, 1 and 2 are dependent on the first two instructions. And since it says that like the result of a load instruction can only be forwarded from the write back stage to the execute stage. So we will want to put the execute stage of this add instruction here, the same cycle as the write back stage, because of the forwarding and the internal register file forwarding, that we can access the newly written data at the same cycle as as it is written. So we can have the fetch, the decode, but yeah, we have to store the pipeline for one cycle because we have to wait because the execute stage have to wait for the write back stage of like the second load instruction. And then for the store word instruction, sorry, this should be memory and write back. For the store word instruction, it's also dependent on the add instruction, but since it's an add, not a load word, the result can be forwarded from the memory stage. So we should have the execute stage here, the memory stage, and the write stage. Then for the subtraction, we don't have dependencies. And for the branch instruction, we have the dependency on register 4, so it will also have to wait. Yeah, sorry, we should also have a bubble here. And yeah, this is getting a bit messy. Okay. So now for the last question, we want to calculate the number of cycles it takes to execute the code segment on machine B. Wait a minute. Let me check. Yeah, so yeah, this is like, yeah, sorry for like this mess. So for the subtraction in instruction, because like this fetch stage is stored, this fetch stage will yeah, let's just like move every column down. This fetch stage will happen here, and decode, execute, memory, write back. So oops. So this goes to here, and this goes to yep, Yes. Okay. To calculate the number of cycles, we see like how long does every iteration take, and remember that we will still have to wait one more cycle for the branch PC to be resolved. So for the first instruction of the next iteration, it will happen here. So as you can see, it takes 8 cycles for a iteration. So 8 times 100 plus another 3 cycles to drain the pipeline at the end of the execution of the program. So we have 803 cycles for the entire program. Yeah, so that's all for this question. Is there any question, comments? Yeah. Okay, and thank you very much for the feedback. We will discuss about this. Thanks.
Can you hear me well? Can you hear me? Yes, you can. Okay. So we're going to solve together the question on Tomasulo's algorithm. This is a question that usually is in the exam every year, I think. And it's mostly reading it in the beginning and paying attention to what it says, the information that we give in the instructions. And then the question, I think, if you understand the algorithm and what is the reservation stations, the execution units, etc., and the register naming, then you will be able to solve it quite easily because the questions after you read it are quite similar, I would say. So let's read together. So it says in the beginning, we consider an in-order fetch out-of-order dispatch. The out-of-order dispatch is what makes it also the Tomasulo's part of it, makes it the Tomasulo's algorithm and the out-of-order execution. But we have in-order retirement of the instructions. So the engine has 4 stages: the fetch, decode, execute, and write back. The engine can fetch 1 instruction per cycle, decode 1 instruction per cycle, and write back the result of 1 instruction per cycle. So we have the important in this exercise is this information. We have an adder that executes add instructions and a multiplier which executes multiplier instructions, multiplications. So this is really important. And don't be confused here. It's not the same thing as having reservation stations. It's different having the execution units, different having different number of reservation stations. So I'm saying that so that you don't confuse during the exam. So the execution units are fully pipelined. The adder has 2 stages, E1 and E2, and the multiplier has 4 stages, E1, E2, E3, and E4. And the execution of each stage takes 1 cycle. The adder has, this is the second most important information, the adder has a 2-entry reservation station, and the multiplier has a 3-entry reservation station. So when we want to execute add instructions and we'll have dependencies, then we will use the reservation stations to dispatch the instructions of the adder. And we use the separate
reservation stations for the multiplier. This is critical to solve the exercise correctly. It says the instruction always allocates the first available entry of the reservation stations of the corresponding execution unit. This information is helpful, maybe not in this exercise specifically, but it's helpful if you need to find out the order of the dependencies or some order of the instructions, because this is how you will understand the register renaming inside the reservation stations and how the instructions were adding up entries in the reservation stations. So the next information, full data forwarding is available. During the last cycle of the execution stage, the tags and data are broadcast to the reservation station, the register alias table. So to remind you, the register alias table gives us information about the dependent instructions, the dependent registers from the reservation stations. It says here, an add instruction updates the reservation station entries of the dependent instructions in the E2 stage. So the updated value can be read from the reservation station entry in the next cycle. Therefore, a dependent instruction can potentially begin its execution in the next cycle. This is not important for the exercise. You just need to keep in mind that the register alias table will give us the dependencies with the reservation station entries. So the multiplier and adder have separate output buses, which allow both the adder and the multiplier to update the reservation stations in the RAT in the same cycle. And the last property, an instruction continues to occupy a reservation station slot until it finishes the write back stage. And the reservation station entry is deallocated after the write back stage. So let's go right now to the problem definition. This was the system configuration, right? So the processor is about to fetch and execute 5 instructions. So read this carefully because some student at some point thought it would execute 7. I remember correcting this. So assume the reservation stations are initially all empty, and the initial state of the register alias table is given below in figure A. So what we see here, we see that all the registers are valid and all the registers have some value, right? And you need to be careful about the values because this is how you need to reverse engineer in the following question that I will show. So instructions are fetched, decoded, and executed as discussed in class. And at some point during the execution of the 5 instructions, you see a snapshot of the state of the reservation stations and the register alias table, which is B and C. So as you can see right now in B, we have some registers which are not valid. And why are they not valid? Because they're waiting for some, they have a dependency. We need to execute first some instruction and then update the registers. And as you can see in the tag, we see the registers and we see the dependencies coming from the reservation stations. For example, register 4 is invalid and its value depends on the execution of A in the multiplication reservation station number entry number 2. Okay, this is really important to understand. So spend the first minutes to understand if there is a similar question, to understand the information given in these figures, like the initial state of the reservation of the register alias table, the final state of the register alias table, and the intermediate, the snapshot of the reservation stations, to be able to understand what's going on. So as you can see also, okay. Okay, we can start with the question. So what it says in the beginning, let's say we need to create a data flow graph. So based on the information provided above, identify the instructions and provide the data flow graph below for the instructions that have been fetched. Please appropriately connect the nodes using edges and specify the direction of each edge. Label each edge with a destination architectural register and the corresponding tag. So to begin with, the way you would start thinking about this is we need to think as we have some inputs, the registers which are used in the beginning. We have some operators, pluses and multiplications at this stage in time. So we have, in the beginning, we have all the registers, right? All the registers which are valid. So as you can see here, we had some registers which are valid, which is register 0, 1, 2, 3, 6, 7. Let me make it with red. It's 1, 0, 1, 2, 3, 6, and 7. For sure, you're going to need these for the inputs, right? We need to start with these registers because all the other registers have dependencies. So what I would do if I were you, I would start with R0, R1, R2, R3, R6, and R7. Okay. So how do we start? We need to figure out first that you need to simplify it as much as possible. So start by what you consider obvious. So if we go back and see here in the plus the reservation station for the others, right? You can see that we have two ready registers which need to be added together, right? And they produce the renamed value L. So which are the values of these two registers? The first register has the value 82, and the second register has the value 1. So then you need to go back to the initial state of the RAT and ask yourself, so to which registers these values correspond to? So we have register R1, which has the value 82, and the register R2, which has the value 1. Okay. And then you go and ask, okay, and which register is L going to update? So L is going to update register R8, right? So you start simply like this, and then you need to do the following. So we need to combine R1 and R2 to produce the result for R8. So the way you would do it is this. R1, R2. What operation are we doing? We're doing an addition, right? And what do we produce? We produce the result for R8. And how do you show this? You show that we produce the symbol L, which corresponds to the output for R8. So this is the simplest, I think, we have in this exercise. And then you need to track and understand the more complicated dependencies. So let's go back. So let's try to see if we see anything else familiar. So for F, what do we see? So for F, we see that we have two valid registers, a register with the value 45 and a register with the value 1. So which register has the value 45 in the question? So the register with a, yeah. You can say. Yeah. And which is this operation? Correct. So, as your colleague said, we have an operation that updated register R3, which is done before the snapshot, and we added R4 and R7 because it's the only combination that can produce the result 45. So the only register that has changed is R3, and this is the first operation that we need to point out to be able to continue with the rest of the dependencies. So we have R4 as well, which is coming from a previous snapshot, this R4. This is not the final R4, right? And we want to perform a plus operation between R4 and R7. Again, I repeat, R4 in the initial state has the value 10, and R7 has the value 35, which ends up being 45. So the symbolic name here is not shown because the instruction is already executed. You can name it, let's say X, whatever. And we update the register R3. So this R3 is really important right now because it's gonna be needed to identify the rest of the dependencies. So let's go back. So let's find the F, right? Which register is this one? This is R3. And which register is this one? This is register R2. So we know that F is going to be produced by multiplying registers R3 and R2. So we can show this here. The new R3, right? So we have we need to multiply the result that we received from the addition of R7 and R4, which is the content of R3, with and combine it and multiply it with the content of R2, which is 1. And this way, what do we produce? We produce F. And where is F? Which register is F going to update? It's going to update R5, right? F is going to update R5. So the output is the symbolic name F, which updates the register R5. So let's try to go for the next dependency. So we have A and B, right? So for A, what do we see? We depend on the tag F and on 10. So the tag F was produced, is right now the content of the value of the register R5, right? So it's the value that will be produced here. And 10, as you can see, 10 is again the value of R4 because that register hasn't changed. Sorry, yeah. So we need to multiply 10 by, which is, you can write it here as well if you want to remember it. It's fine writing the values. Just point out that it's a value, right? Which is multiplied by the content of R5 from the symbolic name F. And what do we output? We output A. And where is A? What is A updating? It's update R4 itself. So you need to point out here the label A with R4. So we have only one that is not defined yet. So we have B, one valid register with the content 23, and another valid register with the content 45. So with the content 45, we already know that it's the register 3. And with the content 23, it's the register 6, as you can see here. So what we can do is we need to come here and say the R6 needs to be combined with, be careful here, it's this one, it's the output of, it's X here, the R3. It needs to be multiplied in order to produce B, which you can see here, B is gonna update the register R9. So here, R9. Yes. So this is I think it's quite simple, this one. Sometimes it's more complicated, sometimes it's more simple. Any questions on that? Because then the next one depends, it's easy, it depends only on that. Just be careful with the nodes and try to understand well the transitions between the register alias tables and the contents of the reservation stations. Spend more time understanding it rather than starting the schematic and the data flow quickly. Okay. We can go to the second question. So we need to fill in the blanks below with the 5 instruction sequence in program order. And there can be more than one correct ordering. When referring to registers, please use the architectural names are 0 through R9 and place the register with a small architectural name on the left source register box. So be careful here. Do not write values instead of registers unless you need to. Like you need, because we do not have immediates here. We don't have an add immediate. We have an add between registers. So do not start writing add to R8 10, 25. Like that doesn't make sense in the ISA. We need to add registers, not values. So what is the first instruction that we needed to execute? The first instruction was, as we did in the beginning, was the R7 with R4, which adds to R3. There is one more instruction that we can, okay, let's put it in another context. So which instruction can be executed at any point in time? That doesn't matter. The instruction is we add, yes, you can say. Yeah, so R1 and R2, which add up to R8, it can be executed at any point in time. Yeah. Yes, that's true. Yeah. Or not. I mean, after the add, after the first add, not. It cannot be before the first add, right? It needs to be after the first addition to the R3, R4. So the first one, yes, it's the add, as we said, it's the add to R3, which was executed before the snapshot. We add R4 and R7, and we add it to R3. So what we did next is we multiplied the content of R3 with the content of R4 to produce the value of, no, actually, no, we didn't do that. We multiplied the content of R2 and the content of R3 to produce R5. So we need to multiply the content of R3 and the content of R2. So here, the order between the registers is fine. Like you can put it, if you do a mistake, we're not gonna cut any points. Like it's fine because it's the same operation essentially, right? Even though in the reservation stations there is an order, even if you don't write it correctly, like I'm not gonna cut any points. So, and we update register R5. And then what we did is we took the value of R4, we multiplied it with the R5. So we put it to R4. We multiply R5 with R4. So here, as I said, this one, it can be anywhere, right? After the first one though, after the first one. So it needs to be either here, 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 or here. So I would add it at the end, it's more safe. So I would add it at the end. And then we have one more multiplication to produce R9, which is using R3. So be careful about that. It needs to be after the first instruction. So R9 is using R6 and the result from the first addition. That produced R3. So this is the execution of the program. Any questions? I think if you understand the data flow graph, if you would understand the data flow graph in this exercise, you would be easily writing down the program. Yeah, the goal here is to test whether you can understand the concept of reservation stations and the register alias table for the Tomasoulous algorithm. Okay, thanks. Yeah, sorry.
Okay, I guess you can hear me. So this question is about GPU and SIMD, mostly about to calculate the SIMD utilization rate. So, so in this question, we have a GPU that the warp size we consider it has, 32 threads here, and we have 32 SIMD lanes. So it means that a warp can be executed in one cycle completely. So we have 2 codes here, and there are some questions regarding each code that we are going over them. So the important thing about this code segment is that so the instruction inside the outer loop, each of them is only one instruction. So basically, we assume that those, for example, addition instruction like array I plus equal to array I plus 1. So it's kind of, you consider that, the values are already in your registers. You don't need to load them from the memory. So basically, they are only one instruction. So we have basically 4 instructions inside the outer loop. And each iteration is assigned to one thread. So this is the basic explanation of this question. So the first question is that how many warps does it take to execute those code segments? So basically, it is actually the easiest part of this question. So we have, so each 4 has 1024 iterations, and we assigned each iteration to one thread. So basically, the total number of threads that you need is 1024. And the warp size is 32. So basically, the number of warps that we need divided by 32, which is 32 warps. Is it clear? I think so, yeah. So the second part is about, as I said, SIMD utilization. So it's asking that what is the SIMD utilization of the first iteration of the inner loop, which means J equals to 0 for code segment 1. So let's take another look at this code segment. So in this code, we initialize the S to 1. Here we have a condition. So whenever you have a condition, you should think about it. If all threads in a warp are going to execute, are going to take that branch, or some of them are going to be not taken. So if all threads of a warp basically take the branch, we have like 100% utilization for that warp. And if non-threads, no threads in that warp basically take that branch, then we don't need to schedule that warp for the execution. So again, we don't waste our SIMD lanes. So the inefficient part is that some threads in a warp take the branch, and some of them basically do not take the branch. So then we have some, loss in our utilization. So here the branch is checking if I, the mode of 2 multiplied by S is basically equals to 0 or not. Divisible or not. So for the first iteration, that J equals to 0, basically S is 1. Then here we only check that I is even or odd, which means if our thread is in, the thread ID is even, we take this branch. And if the thread ID is odd, we don't take this branch. Okay. So in order to calculate the SIMD utilization, you should first see basically how many instructions at the best case, at the best case, if everything goes smoothly with no branch, needs to calculate this instruction. So here we have like 32 warps based on the previous part, and each warp has 32 threads. And in this for loop, we have 4 instructions. So this is the total number of instructions that could be executed in an efficient way. But for each warp, because in each warp, like 16 threads are even and 16 of them are odd. So we can say that basically in each warp, like the 32 warp, the 16 threads execute 4 instructions. But the other threads, basically, they execute 3 instructions. Those that do not take this branch, they just need to execute the last instruction. So if you simplify this equation, you reach to 7/8. Is that clear? So no, actually it is 7/8 because I consider the first iteration, J equals to 0. Because when J is 0, basically S is 1. For every I, exactly. Because basically in the explanation say that J is stored in registers and is local for each thread. Yeah. No, not J, S. S resides in a register and is private to each thread. No. No, this is this S equals to 1 is kind of initialization before launching our GPU kernel, let's say. So we initialize S to 1, and we make a kernel that has like a grid that has 1024 threads, and we just invoke that kernel. And in the kernel code, we have only these 4 instructions. And it is important, basically, when you want to calculate the SIMD utilization, you just need to consider the kernel code. It's not important. The initialization was in the CPU side, not in the GPU. Okay, so then we have 0. So I basically is a thread ID. Okay. Exactly. For each thread. Yeah. Yes. Exactly. Exactly. No. So basically, in GPU, threads are running in parallel, or yes, in parallel. So each thread execute in serial. So you can, so I mean, these 4 instructions are executed in, in a serial manner for each thread. But threads are, are executing in parallel or concurrently, let's say. It's not visible. And actually it is in the, based on the explanation of this question, S resides in a register and is private to each thread. So basically each thread has its own version of S. The only shared, the only shared memory is the array A, which actually we don't care here because we say that we move array A to the registers. And the question specifically said that the code segment are correct. So do not think about any correctness issues and those stuff. So you don't need to be worried about that. Any other questions? Yeah, sure. So in part C, we have the same question as part B, but for the code segment 2. So let's take a look at code segment 2. Again, we are going to calculate the SIMD utilization for the first iteration of the inner loop, which means j equals to 0. So here in code segment 2, we initialize S to 512. And in the conditional branch, we, the condition that we check is that I is less than S. Okay. So the number of I, which is the thread ID, could be from 0 to 1023, which means that for those threads that their ID is less than 512, all of them are going to take this branch. And for those threads that their ID is from 112 to 1023, none of them are going to basically take this branch. So based on my explanation, I guess you can assume that the SIMD utilization rate here is 100%. Because for the first 16 warps, why I'm saying 16? Because 16 times 32 is 512. So for the first 16 warps, all of the threads inside the warp are going to basically take this branch. So all of them execute 4 instructions. And for the next 16 warps, again, all of them are going to execute 3 instructions. So we don't have any, waste in our SIMD utilization. So if you want to write it down here, you can say that, okay, I have like 16 warps. Each of them has 32 threads, and they run 4 instructions. And again, we have 16 warps, 32 threads, and they run 3 instructions. And here also, basically, you need to repeat the same. So which means 100%. So for this part, basically, you don't need to write an equation. Just, write and your intuition about why it is 100% would be, enough. Yeah. Exactly. Mm-hmm. Yeah. Yeah, the difference is that in the second code, in code segment 2, there is no warp that, at least for S equals to 512, there is no warp that have some threads are active and some of them are inactive. So this is the main difference. As I said, whenever you have a warp, you prefer to basically schedule all threads of that warp for the execution, or basically you do not schedule. So that means that you use your SIMD lanes completely, or you do not use them again completely. But whenever you have like some of threads active and some of them inactive inside one warp, then you have to schedule that warp, and you are using that SIMD lane like partially, which wastes your resources. Yeah, I'm not sure if I got your question correctly. Uh-huh. Exactly. Exactly. Yeah. Mm-hmm. Mm-hmm. Yeah, it's still. Yeah, still, I'm not sure if I understand your question. I will be around. We can also chat later. Okay. So in part D, yeah, it's actually, I would say, is the hardest part of this question. He said that it's asking what's the SIMD utilization of any iteration of the inner loop. So basically, J can be from 1, can be from 0 to 10 to basically to 9. So you should come up with an equation that equation should tell you what's the SIMD utilization. Okay, let's see. So here in each iteration, we basically shifts left S by 1, which means that we multiply it by 2. So here, this condition first checks that if I is divisible by 2. In the second iteration, checks that if it is divisible by 4, 8, 16, 32. So until 32, you can see that basically the thread ID, of all warps, you can consider that them from 0 to 31. So until 32, you can imagine that all warps, they have at least one thread, one active thread. But when it goes to 64, then we have some warps that they have only one active thread, and some warps that they don't have any active thread for that slot. So I'm telling you this because it can help you how to define that equation. Actually, this is from the hint, which may be piecewise. Okay. So let's write something here to solve it. So when J is 0, we are checking and S is 1. When J is 1, then S is 2. So you can come up with the equation like this is like 2 power of J plus 1. And when J is 9, basically it is. So the if equation checks if it is divisible by 1024 when J is 9. Okay. So until J equals to 4, here it is 2 power 5, which is 32. So let's write the equation. So until this part, we have this like so we have 32 warp. Each warp has 32 threads, and each of them should run 4 instructions. Why I'm saying that they should run 4 instructions? Because all of these warps, there should be at least one thread that thread basically takes that branch. So we have a warp, we check the if, some threads, which at least one of them takes that branch. So we have basically that warp is executing 4 instructions. So this 4 comes here because of that. And here in the top, we say that we have 32 warp. Then we should write the number of threads that they take 4 instructions. How many threads we have? 32 threads divided by do you agree? So it means that if J is for example, when J is 0, we were checking that if it is divisible by 2 or not. So like 16 threads, they would take the branch. So here we calculate like 32 by 2 power J plus 1, which is like 32 by over 2, which is 16 again. And all of these threads, they take 4 instructions. The remaining threads, which is like 32 warps times 1 minus times 3. These the remaining threads, they take like 3 instructions. So if you just simplify this equation, you don't need actually to simplify it a lot, but yeah, maybe you can. Yeah, for example, we can cancel out 32. So here we have 4 over, and we have plus 3 minus, then we reach to so if we, for example, for part B, that j was 0. If we consider j equals to 0, we have 1 over 2 plus 3 over 4, which is again 7 over 8 that we had in part B. So this equation is correct for basically j greater or equal 0 and less than 5. Are there any questions for the first part of this part? Yes. Sorry. Yeah, because exactly. So because when j is 5, then in the condition, you are checking that if I is divisible by 64, for example, then it means that basically there should be some warps that they don't, no threads of that warp is going to take that branch. Is that true? So when it is 64, it means that the first thread of the first warp is going to take the branch. Then the second warp, no threads. The third warp, again, the first thread is going to take that branch. So because of that, we need to basically, we need to separate these two equations. So when j is greater than 5 and less than 10, the difference is that there should be only one thread in some warps that is active, and there should be some warps that they don't have any active threads. And the number of that warps basically is divided by 2 by each iterations. So let's see. So for this part, so you have like the total number of warps is 32 divided by, so when j is 5, how many warps do we have? Like how many active warps do we have to run that 4 instructions? Is 16 basically. So for 5 is 16, which means that we need to divide 32 by 2. So here it means that I would say 9 minus j. So this is the number of warps times 32 thread times 4 instructions. So here, the other warps, they have like, again, 32 threads, but they execute only 3 instructions. And here we have again, we have like 32 divided by only one thread, execute 4 instructions. Other threads, which is 31, they execute 3 instructions in those warps. And again, we have the same equation like here. Is the equation clear? Yeah, it could be a bit confusing, but I hope you get the whole idea about how to write this equation. So, yeah, I'm not going to simplify this equation. You don't need actually to simplify it a lot in the exam. If your equation makes sense, then that's all. You don't need to basically solve it until the end. Okay. So the part E is asking again the same question for code segment 2. So remember the difference between code segment 2 and code segment 1. For code segment 2, so we have this S, we basically initialize it to 512. And in each iteration, we divide S by 2. So let's keep the track. When J is 0, S is 512, which is 29. When J is 1, S is 256, which is 28. And when J is 9, it should be 1. So we can come up with this equation, 2, 9 minus J. Okay. So for this branch, for this if condition, remember we were saying that like there are some warps that they don't have any threads to take this branch. So if until S equals to 32, we have this condition, because like for example, for 64, again, we have like 2 warps that they completely, all threads of those warps are going to be executed. And for other warps, because they basically their thread ID is greater than S, none of threads of them are going to be executed. So it means that until if S32, which means that until J equals to 4. So for J equals to 0, J equals to 1, and 4. For all of them, we have 100% utilization rate. But starting from J5, when J is 5, then S is like 16. Then there should be the first warp has some threads that are going to take this branch and some threads that are not going to take the branch. So basically our utilization rate starts decreasing from j equals to 5. So what you should say here is that like we have 100% utilization rate for j greater or equal of 0 and less than 5. And for that part, let's write an equation again. So for that part, you have one warp. Yeah, exactly. So you have one warp that has 32 threads, like one warp times 32. That it needs basically all of these threads, they need to run 4 instructions, but unfortunately they don't. Some of them because of the if operation. And the other warps, like the 31 warps, they have 32 threads, and all of them they execute 3 instructions. Okay, this is the bottom, and in the top. So one warp, it has like 32 threads divided by again 9 minus j times 4 plus that warp remaining threads of that warp they have 3 instructions, and other warps they have 3 instructions. So if you write this equation, then basically you answer this part again. Does it make sense? Okay. So in part F, we have, is there any iteration where both code segments have the same utilization? So it is actually, I would say, a bit obvious. Like, so for this part E, until J4, the utilization is 100%. And after, like, when you increase the J from 4 to 9, so you have less utilization rate. For part D, your basically your utilization rate cannot be 100% in any case. So the answer should be in the second part for sure. Like J should be greater or equal 5 and less than 10 for sure. And if you check these two equations, this equation and this equation, you can see that if I put J as 9, basically both of them are completely the same. Are they? Yeah, I think so. If you simplify them, they are completely the same. So, so the part F, J should be 9. Do you want me to simplify to make sure? I don't think so. Okay. And part G, which code is expected to run faster on a GPU? So the one that has usually the code that has less branch, that has a higher SIMD utilization should be run faster, because whenever you have a higher utilization rate, it means that you are scheduling warps more efficiently. So the total number of warp instructions that you are executing is less. So I'm not saying that it is always the case. There should be some, because you always can, like, yeah, exactly. If the workload is completely the same. So these two code, they are actually doing the same thing. If you check them, the code segment 1 and code segment 2, both of them are doing the same. The difference is that how you are accumulating, the array A. So the overall, the difference is how basically how you organize your memory accesses. So for this code, for this specific example, because code segment 2 has higher SIMD utilization than code segment 1, except the last iteration, which is J9. So we expect that code segment 2 runs faster. Was that clear? Any question? Yeah. Mm-hmm. Yeah. Yeah. So actually, yeah, we had this similar question, I guess. So the thing is that S is private to each thread. So each thread has its own version of S. So basically, all threads, they see like S. When they start executing, they see S equals to 1. So yeah, is that clear now? Yeah, the thread itself changes, yes. Oh, that even I said was only for the first iteration. I said that, yeah, for the first iteration of the inner loop, which was the question part B, J equals to 0. So for that, yeah, only even threads are going to take the branch. Yeah. Sure. So I would suggest that you go over this question. We have a similar kind of this GPU SIMD question in the past exams. I would say that this one was the hardest one. So if you can completely understand this question, I think you should be able to solve this kind of questions. So don't worry. And I will be around to answer more questions about that for sure. Okay.
Okay, hi everyone. Do you see things well? I think so. Okay, so let's start with this question. Oh. Is this one? No, this one? This one? Can come help? Oh, this one? Like this? Like this? So, do you hear me better? Okay. Let's start with this question. Branch prediction. You're given the following piece of code that iterates through two large arrays, J and K, and each are populated with completely, meaning truly random positive integers. The code has 5 branches labeled from B1 to B5. And when we say that a branch is taken, we mean that the code inside the curly brackets is executed. And assume that the code is run to completion without any errors or interruptions. There are no exceptions. Basically, it means that the code just runs smoothly and it finishes. So for the following questions, assume that this is the only block of code that will ever be run on the machines, and that the loop condition branches is resolved first in the iteration, which means that the if statements execute only after resolving the loop condition branch. So this is the loop, right? It means that we will first know if we need to, we resolve the condition here, and then we go to these guys. So, and these are the branches. So let's take a look. So it's the for statement. So the for loop, sorry. And that's the first if, second one, third, and fourth, right? So you're given 3 machines whose components are identical in every way, except for their branch predictors. So machine A uses an always taken branch predictor, which is like a very simple always taken over and over. Machine B uses one single level global 2-bit saturating counter branch predictor shared by all branches, which starts at weakly taken. And machine C uses a pair branch 2-bit saturating counter as its branch predictor, and now all counters start at weakly not taken. And here's the saturating counter values. So you have strongly not taken. So for our solution, let's call it S&T. And then weakly not taken, WNT, and weakly taken, WT, and strongly taken, okay? So basically it means that if you are weakly not taken, but then it turns out that you have to actually take the branch, then you first go to weakly taken. And then if again, you realize that, oh, you actually need to take the branch for the next one, you go strongly taken. So you gradually update your confidence in prediction. So let's see what the questions are. So it says that, good. Answer the following questions. So it basically for all of them asks for misprediction rate when the above piece of code runs on machine A, B, and C. So we need to figure that out. And for A and C, it's like very easy, right? It always does one thing, or this is like a local one. And for B is the one which is a little bit more detailed because it's a global history. So we need to see what's the interaction between different branches and stuff. So let's start with A. What was A? I was like, okay, always taken. So let me quickly, yeah, I can actually do this. So we see both things, for example. That actually looks good. Okay. So we want to be always taken. Let's see what happens. So for this branch B1, always taken is fine all the time, except for the last iteration. So when we go to I1000, then it's like, it mispredicts, right? So B1 leads to 1 misprediction out of 1,001 times that it executes, right? So then B2 gets executed. So B2, B3, B4, B5 get executed only 1,000 times. because in the end, for the 1001st branch, which is like I equal to 1000, it would not go in here anyways. So we would have only 1000 times these guys would execute. And so it's always taken, so it's even and odd. So 500 times would do mistakes. And then for here, the 250 first times it's fine, and then starts mispredicting the remaining 750 times. And for B4 and B5, so it's like this one is like less than 500, and the other one is like bigger or equal to that. So we would have each of them 500 times mispredicting. So overall, your misprediction rate would be something like this. So all of these guys, so if I want to cheat, the number is this. So you can just sum them, that doesn't matter, right? You can write the sum here. And then here we would have 5,000, like overall 1,000 for each of them. And for this one also one extra for I equal to 1,000. So we would have this. That will be overall count of branches, and that will be our misprediction rate. So let's go to machine B, which has, I don't know, like a more complex predictor. So we want to have a single level global 2-bit saturating counter starting at weekly taken. So this solution, I want to, since I want to explain it a bit more, I want to write it in the back of the paper. So it's a global one, right? So here we have part B, which is global and starts at weekly taken. So what would that mean? So it is global, meaning that all branches together would lead to something, like they would change the history together, all of them. So let's take a look at them based on different values of I, right? We would expect to see kind of like same sort of trends for I, let's say, between 0 to 249, right? Because then this branch starts like acting differently. Center it a bit more. Yeah. This one starts like acting a bit differently, right? So let's separate this. So I want to first solve it for that. Then I will solve it for 250 until like 499. And then I will solve it for 500 until 1000. So let's see, let's just like start playing with it around and let's see what happens. And we will see some patterns, and that would help us a bit. So I start with I0 and I'm weakly taken. I go to branch 1, which actually turns out to be taken, so I go strongly taken. Then B2, which is like this even and odd thing. I'm even, so great, strongly taken. B3, it's like less than 250. That's right. And then B4, less than 500. That's right. Right, so I'm strongly taken. Then B5, it's like, okay, no, that's different. So we go to weakly taken, because from strongly taken, you first go to weakly taken. You can like change gradually, right? So that was iteration 0, and then at the end of it, I'm weakly taken. I want to go to iteration 1. Let's see what happens here, right? So this is this weakly taken here. Here comes here. Okay. So B1, great, still strongly taken. B2. No, that's the odd number, so we go weakly taken. That was a wrong prediction, let's say. Then we have B3. Says that, okay, less than 250. That's right. And then B4, less than 500. That's right. B5 again, weakly taken. So when I go to iteration 2, I will be weakly taken again, right? So the pattern would kind of like repeat, because always, I would start either odd or even. I would start with weakly taken, and then I would do the same stuff. So let's see in this scenario how many misses we had. We're doing fine here, except for this one, right? Then let's see what happens here. here was a misprediction, and then here also, right? So this whole combination, let's say this duo happens overall 125 times, right? And overall, we would have 3 misses per duo, per like these 2 lines. So it would be 375 misses so far. Okay. This color, yeah, okay, it shows color also. Okay, let's go to I equals to 250 until 249. Oh, sorry, no, 449, right? That's before 500. 449, huh? Oh, yeah. Yeah, that was like an elementary school mistake. Yeah. Okay. Let's start. So I250, and we start with I250 here with weekly taken, right? So we start with weekly taken, and we go to B1. Okay, it's strongly taken because that's this branch, right? And then B2, what happens is that, okay, strongly taken. And then B3 no longer holds, right? So it would be weakly taken. Then B4, what happens is like, okay, less than 500, yeah, that's still correct, strongly taken. And then B5, we would be, in this case, weakly taken, right? So did we do that correctly? Let's quickly take a look. So we had weakly taken, then we were strongly taken, then B2 was strongly taken, then we went to be weakly taken here, right? Because we're no longer less than this, and then strongly taken, and then weakly taken. Seems fine. Okay, let's go to I251. And let's see what happens. So we start again with weakly taken, relatively happy. So here, B1, again, strongly taken. B2, it's an even odd, right? We're even, so we mispredict, we go weakly taken. And then B3, what was B3? It's like, okay, less than this, no. It's wrong, so we go weakly not taken because we can like gradually reduce our confidence, right? And then B4, it's like, oh, less than 500, that's correct. So let's be weakly taken again. We can go to taken. And then B5, we mispredict because we're like less than 500, right? So we go to weakly not taken. So here's the catch. We do not repeat the pattern again with 250 because 250 happened to start with weakly taken. But then now 252 is going to start with weekly not taken. So we can't rely on 250 to make our decisions, right? So unfortunately, we need to continue with 252 again to see if a pattern would emerge. Okay, so weekly not taken, B1, right? What do we do here? So weekly not taken, B1, so we go to be weekly taken. Then B2, we become strongly taken because it's an even number. And then B3, what was B3? Less than this one? No, weakly taken. B4, less than this one. Wait, are we correct right now? So this one is a weakly taken, right? And then B2, strongly taken, correct. B3, that's a weakly taken because it's like a mistake here, right? And then 200, and then less than 500. Yes, we are less than 500, strongly taken. And then B5, Again, we mispredict because we are less than 500. And then we go to weekly taken. And then fortunately, the pattern emerges, right? Because here we are weekly taken. And then we also started with weekly taken for odd numbers. So it seems like, okay, from now on, this duo is just going to repeat, okay? So let's see which things mispredicted. So this was good. Let's try this one mispredicted, right? So from strongly to went to weekly, this, right? Then here, this was fine. Here was mispredicted. Then again, we mispredicted from weekly taken and went to not taken. And then here from not taken, we went to taken, right? And then here from weekly taken to not taken. So we did a horrible job here in terms of mispredicting. Let's see what happens. So here we saw this guy is non-taken, but it was taken. And this one, we thought it's strongly taken, but it was not. So we went to weekly, right? And this. Okay. So what happens is that we have like, if we had these like good duos, we would be like, again, 125 multiplied by 7. But then one of them, instead of having 3, like one of these even ones or even ones, has, instead of being 3, has 2. So let's remove 1, right? Because otherwise it would not be the same here. So I'm going to cheat here. 874. Sounds good, right? Okay. So let's do I500 to 1000, right? And let's be aware of the fact that for I1000, we only do B1. We don't do other Bs. So let's see what's up here. Okay. I'm not going to show the solution sheet right now. I assume that after all these, you can like remember what each branch represents until probably next week. So let's start with I equals to 500. So I equals to 500 is an even iteration, even I, right? And then the even ones start with weekly not taken. So let's start. So we start with weekly not taken. Let's see what happens. So B1, if this is the one that is like almost all the time is like taken. So we go weekly taken. And then we have B2, even odd thing, right? So strongly taken. And that is B3 is like, is it less than 250? No, weekly taken. Is it less than 500? No, will be weekly not taken. But then finally, after all this time, is it less than 500 or like equal to 500? Yes. So it will be weekly taken. So we start this one with I equals to 501 with weekly taken, right? So B1, weekly taken. Oh, sorry. It will be strongly taken, right? And then B2, weekly taken because it's an odd number. Then B3 would be weekly not taken. It's the one that less than 250. And B4, okay. Strongly not taken. And then B5 is a taken branch, right? Because it's like more than 500. So we go weekly not taken, which is good. Like finally, the pattern again emerges because we again start the even iterations with weekly not taken. So we're kind of happy about that right now, finished. And then for iteration 1000, which is like the special one, which only like B1 gets checked. Again, we start with weekly not taken, which is actually the branch we don't want to take. So again, we're happy about it. So let's see what happens here. How many times did we mispredict? Okay, this one we mispredicted. Weekly taken, this one. And then the weekly taken, we went to not taken this one. Then it was not taken, but it was taken here. Okay, so here this was fine. This was not fine. This was not. Weekly not taken strongly. This is good. 7. Okay. So here we have overall 250 of these duos happen multiplied by 7, and that would give us 175. Right. So let's add these guys. Middle one, this one. Yeah. Yeah. Mm-hmm. 6. Right, so it will be the same, right? 124 multiplied by 7 plus 6 is equal to this, right? Yeah, that's fine. So anyways, you magically add these numbers, or like you can just also add them without adding them if you have the addition, like time problems, but anyways. So that will be our misprediction. Yeah. Good news is part C is like orders of magnitude takes less work than this one. So is there any question about this before we move on? No. Okay, part C is very good. So let's see, what was the question? So machine C uses per branch. Predictor starts at weekly not taken. So if it's per branch, it's good, right? Our life is gonna be like simpler. That's me. Yeah. And we're gonna start at weekly not taken. And this time we don't need to go through interactions of all stuff. So we're gonna start with weekly not taken, which is, so we will take this branch, right? So not taken mispredicts it for the very first one. For I equals to 0, we mispredict because we actually take the branch. And then like, we start like taking the branch forever, and this becomes a strongly taken until the last one, which should actually be not taken, right? So for I equals to 1000, we do, again, mispredict. So B2, let's start. So for I0, it is weekly not taken, but it actually needs to be taken, right? It's an even number. So we mispredict for I0. And then, so for I equals to 0, we mispredict. So from weekly not taken, we go to weekly taken. Then again, it becomes I equals to 1. We are weekly taken, but actually we need to be not taken. Then we go to weekly not taken, and then this loops. And then we continue like forever mispredicting. So here we had like 2 times kind of like mispredicting. This poor branch would have like 1,000 times mispredicted. Okay, let's start with B3. So we're weekly not taken, but actually we need to take it because like we're less than 250. Then we go strongly taken, right? We train our weekly not taken over like these 250 times to be strongly taken. And then when we reach to 250, from that, so imagine here we are strongly taken, but we reach to 250. So let's say to I 250, we arrive, and then we say, okay, like I don't need to take this branch anymore. Why don't I make it weekly taken? And then we go to I 251. And so, okay, I still don't need to take it. Then I can make it weekly not taken, which then I correctly mispredicted. Okay, it's not taken until end of life of this code, right? So we would have three things again here. So for B4, same stuff happens. So again, we start with I0 is wrong because like, oh, it's weakly not taken, but I should actually be taken. So for I0, it's wrong. Then eventually I start being like strongly, the predictor becomes like strongly taken. Okay. But then I 500 arrives and it's okay, like I should be mispredict, I go weakly taken. And then this one again, 501, I go weakly not taken. So overall, again, 3. Let's see what happens with the last branch. Okay. So here, I start with weakly not taken, which is fine because it's like more than 500. So it's good. It's always goes to strongly not taken. So when actually 500 starts, we are at strongly not taken. But then we realize, okay, we need to actually take it. So we go like, how about weakly not taken? And then 501 would be weakly taken. So we are kind of like fine after that because we take the branch, right? So it's 2. So would be 1010 over that overall number that we had. So that will be our misprediction for the last case. Oh, okay. Questions? Okay.
Yeah. Can you hear me, guys? Yeah. Okay, so let's look at this cache reverse engineering problem. So the question goes like this: you are trying to reverse engineer the characteristics of a cache in a system, so that you can design a more efficient machine-specific implementation of an algorithm you're working on. To do so, you have to come up with 3 sequences of memory accesses to various bytes in the system in an attempt to determine the following 4 cache characteristics. So you're given cache blocks. The cache block size could be 8 bytes to 128 bytes. The cache associativity could be 2-way, 4-way, or 8-way. Cache replacement policy is either LRU or FIFO, and cache size is 4 or 8 kilobytes. So the only statistic that you can collect on this system is cache hit rate after performing each sequence of memory accesses. That here is what you observe. So you are given 3 sequences of addresses which are accessed from
oldest to youngest, and for each sequence you are given a hit rate. So we'll continue. Assume that the cache is initially empty at the beginning of the first sequence, but not at the beginning of the second and the third sequence. The sequences are executed back to back. That is, no other accesses take place in between sequences. So thus, at the beginning of the second sequence, the contents are the same at the end of the first sequence. So once you access the first sequence, the second sequence will see the data that is already in the cache. At the beginning of the third sequence, the contents are the same as at the end of the second sequence. So based on what you observe, what are the following characteristics of the cache? Explain to get points. So to get the cache block size, in this question, we have to kind of use the process of elimination and also try out different combinations. So if the cache block, so for this sub question, to find the cache block size, we have to basically explore all the different cache block sizes and see whether the hit rate that is given for each sequence is it matches the hit rate that is given. So if we take the cache block size of 8 bytes, so let's say the first access 0 goes into a particular goes to one of the cache blocks, which can have addresses 0 to 7, and then 16 goes to another block. 24 goes to a new block because 16 we can store addresses up to 23. So 24 is the new block, but then 25 it belongs to the same block, so that would be considered a cache hit. And then you will have 1024 in a new block, 255 in a new block, because these are not accessed before and these are all considered misses the first time. And you will have 1100 and 305. So if you look at the number of hits that you see in the sequence, because if the cache block size is 8 bytes, you will see only one hit, which is 25. So 1 by 8 is not the hit rate that is given in the problem. So let's look at 16 bytes. So here, the addresses that can be stored in a block will be 0 to 15, 16 to 31, and so on. So 0 goes to a new block. Then 16 will be the first, will be considered a miss and will be stored in a new block. But then you will have 24 going to the same block and 25 going to the same block. So these two will be considered hits because the block will already contain the block of addresses that are accessed. And you will have 1024 is a miss and will be stored in the cache. 255 will be a miss and will be added to a new block. 1100 will be a miss and will be added to a new block, and 305 will be a miss and will be added again to a new block. So here you can see that the hit rate is 2 out of 8 accesses, which matches the hit rate that is given in sequence 1. So we have kind of figured out the cache size, block size already. But if you want to try out more, I mean a higher cache block size, you can also try it out. So if you have 32 bytes, then you will have 0 will be the first address that is accessed and will be miss. Then 16 will also go to the same block because it can store 32 bytes. Then you will have 24 and 25 also in the same block. So these three will be considered hits. And then you will have 1024, 255, 1100. This will also go to a new block because can't be put in the same block as 1024, and then you will have 305. So you will have the cache hit rate of 3 out of 8. So as you keep increasing the block size, you will have the hit rate also increases. So if you try out 64 and 128, I'm sure you will have the same result of 3 by 8. So with this, we have kind of figured out that the cache block size is 16 bytes. So any questions so far? Okay. So yeah, let's move to the next question, which is to find the cache associativity. So far what we have, what we know is that the cache block size is 16 bytes. What we don't know is the cache associativity, and we don't know the replacement policy. We also don't know the total cache size. So, so to do this, we have to figure out, we have to again try out different combinations. So we can start with 8-way cache. Okay. So here again, because we have two possible cache sizes, which is 4K or 8 kilobytes. Let's start with the highest cache size, which is 8 kilobytes. So let me draw a diagram of the 8K 8-way cache. So you will have this is 8-way, and you will have a number of sets. So 0 to let's say n sets. How many? What is the value of n? You can figure out easily by doing some math. So you can divide the total cache to get the number of blocks. You have to divide the number of blocks. You have to just divide the total cache size divided by the block size, which is 16 bytes. And to find the number of sets, you basically take this number of blocks and divide it by the associativity. So if it is 8, you will find the number of sets. Okay, so now we have to figure out what where each address in the sequence would actually go in which set it would go. But as a thumb rule, we can see that since it's 8-way and 8 kilobytes, if you do the math on the number of sets and how much the data can be stored, or the different addresses that can be stored in different sets, you will basically figure out that for set 0, you can actually store addresses like 0, 1024, 2048, then increments of 1024 till so any address which would be multiple of 1024 would be basically can go to 0, set 0. This we can also find out using the index bits in the address. So basically we'll see where each of these addresses go. So when the sequence 1 starts, so we'll also measure the cache hit rate for the cache hits for sequence 1. So we'll store 0 here, and then 16 would come somewhere next in the set 1. So 24 and 25 will be cache hits, as we saw earlier. Then you have 1024, which can be placed in set 0, and so which is considered a miss. And then you have 255, which can be placed somewhere in one of the sets, but it doesn't really matter now. And then you will also have 1100, which could be placed in one of the ways basically in here or somewhere here also, depending on the availability of the cache block. So let's assume that it's placed here. So then we also have 305. Okay, so we have a cache hit rate of 2, but let's see the second sequence. So this is sequence 1. Now sequence 2, we have 31, which is the block is already available. So 16 is already there. So that will be a cache hit. Then we have 65536, which has not been accessed earlier. So it will be added to the set 0 because it's also a multiple of 1024. So this is placed in set 0. Then we have, since 65536 is already there, the next access is 65537, so which will be a cache hit. And the next address is 131072, which is 128K, which is not accessed before, so it will get placed in 131 set 0. And similarly, 256K is not accessed before, so even that is a miss, and it will be placed in set 0. Now we have 8, which is already the block is already available in set 0, so it means that it's a cache hit. And we also have 305 is already there from the previous sequence, so that is also a cache hit. So 1060 is not available in the sequence, which will be placed in let's say somewhere here. So that is a cache miss. So we have 4 cache hits out of 8 accesses, which means that it doesn't satisfy the hit rate that is provided in the sequence. So 8-way is still a possibility because we haven't checked the 4 kilobyte cache size. So if you check the 4 kilobytes cache size, then you can actually see that set 0 can basically accommodate addresses like 0, 512, and 1024, and increments of 512. So you will still have addresses like 65536, 128K, and 256K in the same set. And since we don't have any address which is close to 512, we will still store 1024 in the set 0, and the result would be the same. So it even if we assume that for 8-way the cache size is 4 kilobyte, we still get a hit rate of 4 by 8. So this means that we have to discard 8K as a possible 8-way associativity as a possible answer. So then we move to 4-way. So even in 4-way, we have again 2 possibilities. We have 4 kilobytes and or 8 kilobytes. Okay, so let's take 8 kilobytes first. So let me draw a block of for the 4-way associativity, and you have again set 0 to a number of sets. Okay, so here the set 0 can hold addresses like 0, 10, 2048, 4096, and so on. So I mean, I'm trying to simplify the calculation here because I just divide 8 kilobyte by 4-way, and you kind of get the offsets, which can be stored in block 0. So we look at the sequence again. So 0 gets stored in block 0 in the set 0, and then 16 would be in, let's say, set 1. So 24 and 25 will be cache hits. And you also get 1024, which would be stored somewhere in one of the sets here. It's not stored in set 0. And then you will have 255 somewhere, and 1100 and 305. So all these are considered misses because they are cache misses because they are not accessed before. So the only hits that are there is 24 and 25. Now we continue to the second sequence. So 31 sequence 2 hits. So 31 is basically already there because 16 is the block containing 16 is already present in the cache, and that will be considered a cache hit. So 31. Now we go to 65536, which is not there in the cache, and it will be placed in set 0. Then we have 65537, which will be a cache hit because 65536 was just accessed. And then you have 131072, which is not accessed before, so you will place it in set 0. And you also have 262144, which is 256K, which is not accessed before. And now you have 8 as the address access, so which is already available in set 0. So 8 is a cache hit, and 305 is already stored in the cache from the previous sequence, so you have 305. And you already see that there are 4 cache hits which violates the problem statement. So so instead of going further, we also look at we'll look at 4-way and 4 kilobyte. So we have a number of sets, and here because yeah, again, if you look at the index bits of the block address, you will find that you can store set for set 0. You can store 0, 1024, 2048, and so on. So let's go again with the first sequence. So you will have 0, which is a cache miss, 16. Then you will have 2 hits that we keep seeing for the sequence 1, 24 and 25. Then you have 1024, which is stored in set 0, unlike the 8 kilobyte cache, where because of the larger size you could fit it in one of the other sets. Then you also have somewhere you can store 255. Not sure if you can see the sequence. You could store 255 somewhere here in one of the sets. And then you also have 1100, which is not accessed before, but you could place it in one of the sets, either if the slot is empty in this column or in the second column. So let's just place it in the second column. So then you also have 305. Basically, for this you can calculate the set and the offset, block offset, and you can place it in the right set. So, but for simplicity, we are not doing it in this problem because we are mostly focused on what goes into the set 0. So right now we have 305 here. Okay, now we'll closely look at what would be the cache hits in sequence 2. So 31 would be a cache hit because 16 is already there. then you would place 65536, which is a miss, and it will go to the set 0. 65537 is access net next, and that would be placed in this. That would be a cache hit because it is already available in the cache, the block 65537. And then you have 131072, which can also be placed in the set 0. Now the next thing is next address that comes. If it belongs to set 0, then something has to be replaced. So 256K is also a multiple of 1024, and it can also be placed in set 0. Now we have to explore two possibilities for the replacement. We have to check whether the LRU and FIFO replacement policies. But fortunately, in this problem we have both LRU and FIFO would replace the 0 with the new address, because 0 is the first one that is accessed in case of FIFO, and 0 is also the least recently used address. So yeah, so 262144 would be placed in set 0 instead of 0. And then yeah, so 8 is a cache miss because we just replaced the address 0. So 8 would be replaced in instead of 1024. It's the same. I mean, the replacement block would be the same even for both LRU and FIFO. Then 305 would be a cache hit because it's there from the previous sequence and it's not replaced yet. And 1060 is a cache miss and will be placed somewhere, let's say here. So with 4 by 4 kilobyte, you still get a cache hit ratio, cache hit rate of 3/8. But we have to continue looking at the sequence 3 to verify if this holds on. So now let's look at 262145. So for sequence 3, we already have 262144 in the set 0. So this would be a cache hit. And 65536 is also there in the set 0, which is a cache hit. And 4 is the next address accessed, and it was recently replaced in set 0 by 8. So the entire block would be there, and 4 can also be a cache hit. So you have got 3/3 as the hit rate, which is actually not what is mentioned in the problem statement. So you have at this point you can also discard 4-way associativity, and by process of elimination you can straight away answer that it's a 2-way cache. But if you have time, you can also verify with 2-way associativity also. But yeah, so since we have eliminated the other answers, we will continue with the next question. Do you have any questions so far? Okay. So next we look at what is the cache replacement policy that we need to find. What is the replacement policy, whether it's LRU or FIFO? And so far, what we know is that the cache block size is 16 bytes, and it is 2-way set associative cache. So yeah, so with LRU and or FIFO, we still have 2 more variables to find LRU or FIFO. We should still consider 4 kilobyte total cache size or 8 kilobyte. And also we should check for LRU and FIFO. Okay, so let's look at a 4 kilobyte cache with a two-way associativity. So let me just draw this diagram. So this is set 0, and you will have n sets in the cache. Okay, so yeah, so with this, again, you can find the set from the you can decode the set from the address. But if I quickly do it, the set at set 0 can hold addresses like 0, since it's 4 kilobyte and divided by two-way, it can hold 2048, 4096, and so on. And most of these addresses like 64K, 128K, and 256K fall into set 0. So, so let's start accessing the addresses and then placing it in the cache blocks. So you have 0 here, and you would place 16 in the next block because our block size is 16 bytes, and you will get 24 and 25 as cache hits from sequence 1. Then you would have 1024. When 1024 comes, it's still a miss because it's accessed for the first time, and you would place it somewhere in one of the sets and not in set 0. And next comes 255, so you would place it somewhere between that in one of the sets. Then you will have 1100, and 305 should be placed between after 255 in one of the sets. Sorry for the crude way of drawing, but then I hope you understand the idea behind this. So once this is done, you still have a slot left in the, or only one way is utilized in the cache in set 0. So next you see that 31. So at this point we have completely gone over the sequence 1. Now we'll go to sequence 2. So 31 is the next address. So if we keep track of sequence 2 hits, so 31 would be a hit because 16 is already present in the cache. Then you have 65536. Because there is a empty, one of the ways is still empty, we place 65536 in set 0. And 65537 would be a cache hit because we just placed 65536. And now we get 128K as the next address. Now we need to decide which replacement policy to take. So if we go with LRU, let's go with LRU for now. So if we for this address, if we go with LRU, the least recently used was 0 in set 0. So this would be evicted and replaced with 131072. Okay, so that was a cache miss anyway. So then we get the address 262144, which is also a miss because it was not accessed earlier, and it has to be replaced. It has to replace one of these two blocks in the set 0. Now, which one would it replace? Because we just replaced 0 with the previous address. This is the least recently used. 65536 is the least recently used. So we'll replace that with 262.144. Okay. So next comes 8. So 8 is also not present in the cache at this point. So we take 8 and place it in, again, it belongs to set 0. But where should we place it? Because because we have 2 recent accesses and we should find the least recently used out of that. So we replace 131072 with 8. And once 8 is completed, we will move on to 305. 305 is already there from the previous sequence and it has not been evicted here. And we also have 1060, which is a new access, and it can be placed somewhere here. Okay. So 305 was also a cache hit. Now with LRU replacement policy, we still satisfy the two sequences, but let's look at the third sequence. So with 262145, so at this point, the cache set 0 looks like this, 8 and 262144. So we will see the sequence 3 hits. So 262145 would be a hit because it's already there in the cache. Now 65536 comes. So 65536 has to replace one of these two. And we need to look at which one was accessed least recently used. So because there was an access here to the same cache block in the third sequence, it isn't. This one is not the least recently used. The least recently used was 8. Okay. So because we see that it was accessed here and there was an access to this cache block 262144 containing 262144. So we replace 8 with 65536. Okay. So 65536 again is a miss, and it has replaced the previous cache entry. And now we have 4. So 4 is again a miss because with set 0 you don't have 6. It contains 64K and 256K at this point, and you don't have 0. So even that is a miss, and that will probably replace this entry because that was the least recently used at this point. So you only have 1 out of 3 as the cache hit rate with in the third sequence, which is a violation of what the problem says. So again, you can actually kind of eliminate LRU at this point. And if you have time, you can also go and check for the other possibility or other combination of two-way 8 kilobytes, and it still gives an answer of FIFO. So we only checked for one of the combinations here. So LRU with 2-way and 4 kilobytes actually did not satisfy. So so the replacement policy should satisfy all the different combinations that are there. So so we basically eliminate LRU, and then the answer would be FIFO. Any questions so far? Okay. So now the last question is to identify the cache size, 4 or 8 kilobytes. You can access 2 addresses right after the sequence 3. That is, the contents are the same as at the end of the third sequence, and measure the cache hit rate. Which 2 addresses would you choose, and explain your answer? There could be multiple correct answers. So to find this, for this sub question, so what do we know so far? So we know that the associativity is 2-way, and the cache block size is 16 bytes, and the replacement policy is FIFO. So now to find out if the total cache size is 4 kilobytes or 8 kilobytes, we need to and let me also draw the most recent state of the cache if it is 2-way set associative. So okay. Yeah, for that we need to actually do the FIFO also. Maybe let me do it quickly. So this is set 0 and you have multiple sets. So you have 0 stored here, then 16 somewhere, and I'll focus more on set 0 at this point. So if it is 8 kilobytes and two-way associative, then you will have addresses like 04096, 8192, addresses like that going into the set 0. Now 1024 actually goes somewhere in one of the sets. I'll ignore the 255, 110, and 305. Okay, so in the second sequence, we will have 31, which is a cache hit. Then we will have 65536 and 65537. So let me write down the sequence 2 hits. So you have 31, 65537, and 128K would be the next address, and that has to replace in using FIFO replacement policy. So it still goes and replaces 0 because that was the first address that came. So it is 131,072. And then you have 262,144, which is also a new address, and that has to replace this 64K address because that was the least recently that was the first address that came. So 262,144. And then you also have 8 in the sequence. So 8 has to be accommodated in set 0 again, and 8 will replace the first one which came between these two addresses. So it will replace this. And then you have 305 and 1060. So the cache hits at this point are again 3 by 8. And then the next, let's go to sequence 3 quickly. So you have 262,145, which is a hit. Then this is a new address and has to be replaced in the set 0. So if it is, if this has to replace one of these two addresses, and if it is FIFO replacement policy, then it has to replace the first one that came and not necessarily the most recently accessed. So it will replace 262,144 because 8 came after 262,144. So that will replace 65536. So so in sequence 3, you already have one cache hit, and then this is a cache miss, and 4 is a cache hit because 8 is already available in the cache. So that also kind of matches the hit rate that is given in the problem. Now, so the recent for the last sub question, so we have, I wanted to draw the recent state of the cache. So you have 8 and you have 65536. Okay, so so as I mentioned that we need to add 2 more addresses to the sequence to figure out whether the cache size is 4 kilobytes or 8 kilobytes. So if it is, let's say 4 kilobytes, then your set 0 can contain addresses like 2048, 4096, and increments of 2048. But if it is 8 kilobytes, then you have addresses that can go to set 0 like 4096, 8192, and so on. Again, you can decode this using the index bits of the address. So at this point, we need to actually the technique to do to figure out the between 4K or 8 kilobytes is you need to actually find an address which results in a cache miss in both of them, in both 4 kilobytes and 8 kilobyte, 4 kilobyte and 8 kilobyte cache design. But then in one of them, it actually goes and replaces the set 0 block. So yeah, that is the first address. The second address, what we need to, the second address that we need to use is, we need to access the previous occupant of that cache block to see if there is a cache hit or a cache miss. So with 4 kilobyte, we need to find the address which results in cache miss first time with the first address, and also a cache miss in the second sequence, because it has replaced it was the, let's for example take 8 with, if we have a new address in this or in the first or basically in the next two addresses, if we choose an address which replaces 8, then it results in a cache miss. But then we go ahead and the next address would be, we still go and access 8 to see if it is a cache miss or not. But in case of 8 kilobyte, because we choose a new address, it will still be a cache miss. But then if it's not if the set 0 has not been evicted, then it results in a cache hit. So that is how we kind of differentiate between the two addresses and between the two cache designs. So we see that there is 4096 is common across 4 kilobytes addresses which can go to set 0, but we have 2048, so which is not there in 8 kilobytes. So if it is 2048, it actually goes to in an 8 kilobyte design, it will, if it is set 0, it will basically go to one of the sets in the one of the other sets. So it will go somewhere here. But in case of 4 kilobyte sequence or in the system, it actually it has to replace one of these two addresses. And going by FIFO, it has to replace yeah, so if it is FIFO, then 8 came first. So it would replace 8 with 2048. So with 2048, it results in a cache miss in both 8 kilobytes and 4 kilobytes systems. Now, if we choose the second address that we need to choose should basically go and access the previous entry, which was 8, or any address in that block, 0 to 15. Because in 8 kilobyte system, we still have 8 present in set 0. So if we choose 0 as the second address, then this would result in a cache miss, which is 4 kilobyte system. And in 8 kilobytes, you would get a cache hit. So if you access these two addresses, 2048 and 0, or you could also access any of the other addresses in the 4 kilobyte range, which belongs to set 0, that doesn't belong to 8 kilobyte set 0 addresses. And you could access one of those addresses instead of 2048, and you could still use any of the addresses between 0 to 15 to figure out if there is a cache miss or a cache hit. So with this kind of behavior, you can figure out if it's a 4 kilobyte or a 8 kilobyte system. Any questions so far? Okay. No?
Okay, so we will still have 2 more exercises. Rahul and Gagan will come to solve. So as a quick correction, I checked those equation that I wrote. There is still one simple bug. So here should be j minus 4. So all of them should be j minus 4. Here also, here, and this one. So for those that you took a note, please correct them. I will also post a nice and correct equation on Moodle for your references. Rahul, please go.
Okay. I'm actually surprised that you guys are still here. Well, okay, I'm not going to take a lot of time. So yeah. So this was a, I think, yeah, it's viewable. This was a bonus question in the last year. So it's based on the run-ahead execution, which Professor Mutlu has covered in lecture 25, if I'm not wrong. So as this is a pretty small question. So let's get this done quickly. So it says that, okay, a run-ahead execution processor, I mean, hopefully you all know the run-ahead execution by this time anyway, right? So it just mentions that, okay, we have created another processor which has a run-ahead execution, but it's an unintended bug that every other instruction is run-ahead in the run-ahead mode is dropped by the processor after the fetch stage. So basically once we enter the run-ahead stage, you execute it incorrectly. So, and then the question, the following 3 questions ask for this buggy processors, what is supposed to happen with this processor. Okay, so as it says that all other behavior of the run-ahead mode is exactly as we described in the lecture 25A, if I remember correctly. So yeah, and then we need to explain which of these following questions are correct. So the first question says that, okay, the buggy run-ahead processor finishes the program correctly and faster than the non-buggy run-ahead processors. The answer is obviously yes, that it can happen. Why? Because let's say even if the processor is dropping every other instructions, but then it's actually by dropping every other instruction, it's probably finding more dependent memory instructions to execute in the run-ahead mode. So that might be one reason that, okay, it's executing correctly as well as faster than the normal processor which doesn't have the run-ahead execution. Okay, so the second question is that the buggy run-ahead processor finishes the program correctly, but the slower than the non-buggy run-ahead processor. So is this also possible? The answer is yes. Why? Because let's say if the memory instructions are actually present in the alternate instructions that are getting dropped by this bug that is present in the processor, then what might happen is that in the non-buggy run-ahead processors would actually explore much more dependent memory instructions than the buggy run-ahead processors. And as a result, what would happen is that the non-buggy run-ahead processors would run faster because they have explored much more dependent memory instructions in the run-ahead mode. So yeah, this is also possible. The third point is that the buggy run-ahead processor executes the program incorrectly. This answer is definitely no. Why? Because if you recollect, what happens in the run-ahead execution is that no matter what happens in run-ahead execution mode, nothing gets committed. So that's a crucial part of this question, because just because nothing gets committed means that whatever changes that you make inside the run-ahead mode, it cannot be permanent. So it does not affect the program execution correctness. So basically the entire, let's say, mindset of creating this problem is that no matter what happens, it can actually run, like even if you have some hardware bug in the processor implementation in the run-ahead mode, it can actually create the buggy processor to run faster or the slower than the non-buggy processor. But no matter what happens, it cannot actually run incorrect execution. So yeah, so that's the mindset of this problem, and that's the question in a nutshell. Okay, I'll give it to Gagan now. Yeah, it's done. Yes.
Can you hear me? I guess, yeah. Yeah, cool. So this one is the final question. It's on systolic arrays, and we are doing convolution. So it's quite an easy question. So I expect you guys will get like full points in this one. So first we have like a systolic array, which is like 4 by 4, which is arranged in like a spatial manner, which is 2D. And you know how systolic array does it, just propagates like if you have an input, which you provide from the top, and it propagates into O1. And same from the left side, we have another input, it propagates to the output. And inside there's a register which does a MAC operation. So MAC is nothing but multiply accumulate. So whatever value which is there already, it will add and the multiplication of inputs. And that's how this process, and then it will just propagate the inputs to further processing elements. And what we are doing is we are doing convolution. So over here we have like 4 different convolution which we have to perform on the same processing element array. We already give an example of one of the convolutions, which is for the first one. Let's try another one. If you want to do a convolution of input this input with this, you can call it weights, b vector. So in that case, what we do is it's just like dot product of all the values. So in case we need to get this x0, to get the x0 value, we do a dot product of, so it's just a filter. So you get this b0 kernel which moves on top of the input first. So we'll do a multiplication here. So it will be I00 multiplied by b00 plus I01 multiplied by b01. And then we go to the next row. When we do 10, b10 plus I11, b1. So this will give us the output of x00, and similarly we will do for all of these. And the same fashion we do like different vectors as well, C and D. So if we want to map this sort of operation on a processing element, it's easy if I draw it here and show how these values propagate. So for example, we have these. Let's do just the first row and first column. They all are connected. So for example, now we need to do the first convolution for I vector with the A vector. And you can map like you can provide input from the top, or you can provide the weight vector, which is the A vector, whichever way you prefer. So for example, if we give I vector from the top, so we will give I00 here, and from this side we give 00. So yeah, so if you think about this H0, which is V0. So on the first cycle, on H0 we are giving A00, and on the V0 we give I00. So in this PE0, we perform the multiplication of A00 and I00, which is this part, and then it will propagate both the values. I00 will go down, A00 will go further on the right, and if you see in this calculation, A00 is being reused for doing the multiplication for different weights, for W01, W10, W11. So we can go either way. We can first calculate in the row or in the column, and you will see how it propagates. So in the first cycle, we finish this one. And in the next cycle, this A00 is propagated to the PE01. So now if we want to perform this next calculation, we need I01 and A00 is already propagated. So what we do is on V1, we provide I01. So on cycle number 1, on V1, we provide I01. So now we are able to do this calculation. And now if we look at the third one, we again reuse A00. So we already propagated A00 here in PE02. And to perform this calculation, we need I10. So what we do is on V2, we do I02. So in the next cycle, on V2, we give I02. And similarly for PE03, we can again reuse A00. And here we need A11. Yeah, so next cycle we got, is it clear? Or, okay, cool. And now similarly, so now we can go in like the vertical direction as well in the column. And now what's happening is we need I00 and we check like where the I00 is being reused. So we propagate I00. And if you look at this calculation for B0, which I did here for X00, so we need I0. So what's missing is B00. So what we do is like we give B00 as the input to H1. Is it clear? All right, cool. So on the H1, it's happening after one cycle because it takes one cycle to propagate down and it takes one cycle to propagate in any direction. So now we give B0, 0. And now I0 propagates further. And now we can on H2. And similarly, like we did for B00, in the case of when we are calculating Y00, we need, we will do C00 dot product with I00. So again, we can reuse. So it will be here C00. So similarly, here will be D00. Okay. And now we already did all the calculations for, we propagated through all the PEs. So now what we do is like on the first, so this one is not being used. So now we can load the next, we can start the next calculation, which will be A01 here. So we can start with the calculation of this part now. So similarly, we'll do the same thing again. So now we get A01 and you can, sorry, it's really tiny to write, but yeah. So we get A0. Is it clear? Like, can you see it? Because it's a bit hard to write it down. Okay, so now we get A01 here. And now we do it the same manner. Like we can propagate in this, either in this direction, in the same row, or we can go down in the column. So if we do it in a similar fashion, so now to calculate this middle part, we need I01. So on V0, we get I01 here now. I01, this will be I02. This is I11, I12. So now we complete this in the same row. Now we do the similarly in the column. We go down. So for the column, it would be, now we reuse with I01 in the column. So we check like where I01 is needed. Again, it would be in this calculation. So the next element, so we will get B01 here. C01, D01. So we'll keep on doing in this manner. So this one will be A00, A01. Maybe I'll use a different pen. Now we'll get A10 here. So if we start with this calculation, now we can start over here. So A01 will be used for I10, I11, 20, I21. And similarly, it will be used, now we will reuse I10, which will be used for B10, C10, and D10. And now again, we will start with the last one. So we need to load A11 over here. So we will, instead of A01, we'll get A11. And here we will get I11. So we start with A11. Here we get I11. So for the next one, we reuse A11 again. 12, I21. Here we get I22. And now we go for the, in the same column. So we reuse I11. So I11 will be reused for B11, C11, and D11. So if you see, we calculate, we get all the values. And this first PE, P01, P00, will calculate the, we'll have all the sums for weight 0, 0, 0, yeah, weight 0. Next PE it's propagating the results and also calculating 0, 1, all the values for 0, 1. W10 will be P0, 1, 1. And then if we go for PE010, it will have results for over here, yeah. Yeah, so this one will calculate X00 in the next cycle. So everything is pipeline. 0, 1, 1, 0. And afterwards, we also did, for the C, it was Y0, Y 0, 0, Y0, 1. And the next we'll be calculating, which is P30, which is this one. This one will have all the values for Z0, 0, 0, 1. Yeah. So this is how it would look like. So I would suggest, if you want to solve it, the easiest way is to just start with 1, which is like just do the first convolution, do the weights, and everything is kind of like pipeline. So you would do the same for everything else and go in both the directions. First go in the, whichever you prefer, like row or column or whichever, finish that and then start with the next one, and it keeps on propagating. So this is how it would look like. You have any questions or? Yeah, it's an easy question. I hope you guys will be able to do it. Cool. I wouldn't take much time. It's already late.